include all these data acquisition capabilities to make it something that interacts with your computer in real time, no compiling code or uploading. And how we achieve this is by way of a modified bootloader, which is a fork of the OptiBoot bootloader, which already comes with your Arduino Unos and Nanos. So let me, okay. So on the Arduino board, for those of you who are familiar, you have your IDE, you have some function calls, you compile your C code, upload it to your board, and make it run. Now, in embedded systems, if you are an embedded systems engineer, say, you would use registers, which are basically bytes, where each bit has a function that makes the hardware do something. Let's say I toggle this bit, there will be this output pin where 5 volts or the supply voltage will show up. So it's all binary. Now, what the KuttyPy bootloader does is that it allows you to make changes to this register via a computer that's connected to it. So there's no compiling or uploading. You could write some Python code through its Python library and try to light up an LED, or try to read a register, and through evolving complexity, try to read sensors, etc. So let me show you a short demo. This is the user interface that I made for the Arduino Nano. Now what I've done is I've replaced the bootloader of the Nano with my own, and this allows me to, for example, PB5 is the onboard LED, and I could check the input state, oh, it's low. I could make it an output state, toggle the state of the output, all through Python code. And that library it's documented on read the docs. I'll get to that shortly. So yeah, you can see the board here, and as I toggle it, you can see that the onboard LED getting toggled. So it's a very basic implementation that I'm talking about right now. So yeah, these are both 328P boards. So the registry structure, everything on the data sheet remains pretty much the same, except the ordering of the pins. So you just change the layout accordingly. It's all documented on read the docs, where you have simple function calls. For example, you can import the library. Just say set a value to a register, and the board will immediately behave that way. Or read a value from the register. And as things get more and more complex, you can read values from sensors. For example, an accelerometer that's plugged in onto this board, or control robots through a servo interface, hall sensors, etc. So there's no coding as such involved here. You have a data acquisition instrument right out of the box by just modifying the bootloader on your Arduino. So how do we do that? Okay, there's a very simple change that has been made. On the Arduino bootloader, the job of the bootloader is to get the user compiled code from the computer, flash it to your non-volatile storage on the processor, and start running it. In the KuttyPy bootloader, you just have a couple of additional calls to read and write registers without actually touching the program space area. Okay, so if you have a parallel programmer, you can replace the bootloader with the KuttyPy bootloader. Or if you don't, you can just turn another Arduino into a programmer, make the following connections. I'll just run through them. It's pretty straightforward. And you can flash another Nano with the different bootloader. Now it continues to run as an Arduino. The remaining functions are already there. It's just that you can collect data with it. Right. So this is just the implementation. On the C side of things, there is a couple of extra function calls on the bootloader that allow you to read and write registers. On the software side of things, what I've done is just read the data sheet, find out the address of these registers. Let's say you're dealing with DDR, or let's say TIFR. So it has a register, hex 38. So you go to that location and read it. Or if you want to write to it, you write to that location. So the bootloader is only being told that go to this location, write this value, or go to this location, read this value. So just as it's basically like a debugger. And there, you've transformed it into something you can collect data with. Of course, you can add more UI elements to make it a more teaching-friendly tool for embedded, where we don't use abstraction layers. We directly tell students to read the data sheet, where it says, okay, this bit does this. You pick out that register, toggle the bit, and see that the hardware is doing that function. Okay. Now, with this, I picked out a board that is, sorry. Yeah. Now, with this approach, I built another board. All the schematic layout, everything is linked to in my presentation. This uses the Atmega 32 processor instead of the 328P on the Arduino Unos and Nanos, simply because the 32 is more suitable for teaching. It has 4 ports, A, B, C, and D, all of which have 8 pins. So it's more easy to teach because we have complete bytes. And I included included a bunch of LEDs on board, so we can see the changes for an entire register, a whole set of switches, an R2R DAC, etc. So again, this thing will also work with the Arduino IDE as long as you just select the Atmega 32 board. The software can do all these listed tasks. Reading, writing pins, of course, is one. To monitoring sensors, the ADC values, etc. So here, for example, this particular pin, PC3, is configured as an input initially. You could make it an output. You could make it read values. So this is the ADC value. And because everything is in Python, it's quite simple to make data loggers, which, of course, has already been done for you. And here, this is ADC values being plotted as they're being fetched from the processor. Now, this makes it easy for students. For example, if you're building a project with Uno and you don't know if a particular part is working. Let's say I have a robot with a potentiometer that's measuring an angle of some some angle. Okay, and if you don't know if the ADC is working, you would normally bring out a multimeter and measure the voltage at that point. But here you can simply switch to the bootloader mode and quickly check that the ADC values are correct. Or if connected sensors are not functioning or something, you can come and scan for those sensors and check the values here. Okay, now based on this board, I am currently at the University of Calicut, where we're running outreach programs for teaching kids embedded systems. So we have a whole curriculum where we start out with what are decimal and binary number systems, teach them how to convert between these two, then go on to the importance of bits in embedded systems. Then we move on to a whole programming, basics of programming, because see their course includes Scratch, but they're as yet not being taught to use them to achieve tasks. So for example, we initially asked them, can you make a multiplication table? So that's really not there. So we have to start with programming. We go to basics of making tables. Then we move on to plotting. It's all done in visual drag and drop form, no C or Python. So they just create logical segments and make some usable things. For example, a water tank, what do you call that? A pump that fills up a water tank and automatically cuts off the moment a pressure sensor reading goes above a certain threshold. And if it goes below a certain threshold, you would turn the pump back on. So the basic applications that 6 to 8 standard students are able to do, to more slightly fun things like measuring your heart rate, or even this Google's MediaPipe library we've embedded into the user interface. I'll show that shortly, 2 minutes. This is just things that we can do with it. There's also an Android app. Android because Apple requires extra certification, but on Android, since Arduinos is just USB to serial converters, we have this whole UI where you can do everything that the desktop app can do, including C compilation. But because we can't have a C compiler on the phone yet, it sends your C code to a cloud droplet that I have, compiles it, sends back the hex code, and uploads it to your device. Then there's visual programming. This is built on Blockly, and there's a bunch of blocks for toggling bits, reading registers, etc. And for example, if you want to read a sensor, which is this Max 30100 pulse oximeter sensor, has become really cheap since COVID, about 100 rupees. This is all that you need to do. You need like a block for reading the values. You plug it to a plot block, and then you just keep repeating. So you'll get these plot values. as a whole set of sensors that are compatible. Yeah, you can control robots and things. That's the whole list of sensors that so far have been supported. So the device only speaks on the I2C bus. All the sensor-specific code sits on your Python library or your Android app. And the code is, of course, since it's Python, it's like 2-3 lines of code just to read information from a particular sensor. So here it's just, initialize this TSL2561 light sensor, read the values from it, and just plot it on the screen. So it's like 3 lines of code. Right, I can show you one sensor. So I've plugged in the board with an accelerometer sensor on top of it, which is this MPU 6050. Just go and launch the UI. And here, if I scan for sensors, which is here, I'm sorry. Yeah. So there is a scan button here, which will simply go on the I2C bus and search for sensors that are available. Then you can start fetching readings right away. Now, the usability of this in, for example, a physics lab setting is that you can use Python's libraries like SciPy to extract more meaningful information from this. For example, if this was part of a pendulum and it was oscillating back and forth, let me pretend it's oscillating. Right? So this is GY. You can see the oscillations. And I can pull up the data logger. So where you can visualize these oscillations. Now, if you wanted to know the frequency, you could select a particular sine wave from these. It's not a clean sine wave, but SciPy will still sort of fit something. And say sine fit. There. So I have around 1.5 hertz oscillation frequency, which is extracted from all these data points. And of course, we have demos written where you can programmatically fetch readings and then feed it to SciPy with a standard a sine omega t plus phi function and fit information. So the fit is pretty decent for this sort of poor, noisy data. But it finds applications. So far, we're looking at a very low-cost system. Like you have your Nano or your Uno, which is nowadays like 300 rupees or so. You have an accelerometer, again, 150 rupees or so. And you're already looking at digitizing readings from a pendulum and getting second or third decimal precision when it comes to time period measurement. In your schools, you have this simple pendulum where you use a stopwatch and you take 20 oscillations and you still end up with barely first decimal precision. So this gives you much better control, much better automation. And there's also an IDE, which is very basic at the moment. I still need to work on it, which has we wrote a bunch of examples which focus on registers. Right? Instead of having digital write, digital read, things like that, you go and say, okay, DDR, pin B, ampersand, whatever masking that you need to do. So that's there. Then there is your visual coding, which is, like I said, based on Blockly. So here, it's pretty simple. Read ADC from A1, plot versus time, to it 200 times. So when you run that, you're actually getting the plot of noise from the ADC. This is sort of a work in progress, but I think sensors. Yeah, so if you were to deal with sensors, not sure this works yet. Yeah. So when I click the scan button, the sensor was detected. Now I can select the parameter that I want to log, for example, GZ, or let's say GY. And say. So now it's recording values from the accelerometer in my hand. So this is all part of the series of workshops that we conduct for school kids to get them more interested in this sort of thing. Right. And we have a bunch of sample programs for different things. Okay. This whole board is designed with KiCad. And all the UI elements that you see are built with PyQt. PyQt Graph does all the plotting, SciPy and NumPy for analysis. You'll find the docs at KuttyPy.readthedocs.io. For Windows, I have a compiler installer built with PyInstaller. If there are people who do use that. Let's say KiCad drawing. I have it somewhere here. So KiCad is very powerful, very friendly to use, and this is the board that I was just showing you. And here, it's a nice 3D view of everything. And with this board, I think we trained about 2,000 students, 40 odd workshops, and I figured we'll make something more appealing for 8th graders. So we're working on a similar board, but it's in the form of a turtle. And it has motor drivers, and it can sort of move around. So this is a SEM turtle. Similar approach, but some sensors are already on board. There's a magnetometer on board because then the turtle will know which way it's pointing. So my plan is to implement the logo turtle, but in as a actual hardware, which you can command take 10 steps forward, take 90-degree turns, etc. I think I'll skip this. We're nearing the end of time. Right. I'll skip the video. There is, that's the turtle. It moves around. It can speak to other turtles. Very basic board, again, just like an Arduino, but has a bunch of things on board in addition. Yeah, that brings me to the end of my talk. These are the links for the different things that went into this. I think I'll take questions now. We're at 10:20. These are photos from the workshops that we've been conducting. It's the home page. The docs. There's a workshop page on the docs for Nano. This was at Science Hack Day last couple of years back. And we had a whole setup for this. And that's the page on my personal website for the STEM turtle. I'll take questions now. Thank you.
I heard about KuttyPy, I think, quite long back in PyCon. Yeah, good to see it's kind of making so much progress. So one thing that I didn't understand from the talk is where is the Python code running? Is it kind of running on the computer, or is it running inside the
The Python code is running on your PC, connected PC.
Connected
So the hardware is very minimal. You have the bootloader, which is only about 500 bytes, the original OptiBoot bootloader. To that, there's a couple of function calls for reading and writing registers. That's it. Like you go to a certain location in the memory, read it, or you go to a certain location in memory, write it, and because that refers to a special function register, the hardware will sort of behave in a particular way.
So you basically converted that into an RPC server. Is that pretty much?
Sort of like debugging, yes.
Yeah, you send it, give me this and
fetch. Okay. That's it.
So why is it hard to do the same thing with an Arduino without changing the bootloader?
Why is it hard to do?
I mean, why can't I do the same thing? Why do I need KuttyPy? Why can't I just kind of write?
No, like I showed it in the beginning, you can take a Nano, just replace the bootloader. But the entire software stack, the Python library, allows you to plug and play sensors. It's already written the part for plotting data. Okay. So that stack is there.
Got it.
Right. So otherwise, if you wanted to read data from a particular sensor, you would write a firmware, a sort of state machine to upload to your Arduino. Yeah. Right. And then if you use it for some other purpose, you would have to replace your firmware again. Yeah. Here, this particular section sits in the bootloader, regardless of what code you're running. And you can switch to the bootloader and, tweak and see if things are running fine, etc.
Thanks.
Are there any more questions?
You said the tortoises talk to each other?
I2C.
Okay.
It's
connection.
So this one, I've used these RJ11 jacks, where one leg can be broken off, and you connect a cable from here to here, and you can use this as a sensor bridge, or you can connect this to the leg of another, where one will behave as a slave and the other as a host, like a host-client architecture. So here, if you see, the USB is not connected. It's listening over I2C through one of its legs. The cable is at one leg, and just controlling one from the other. I don't think this 328Ps, I don't know if they can. Well, I've not tried personally, but I don't know if it'll fit, especially the visual programming part. I am planning to explore it, at least for this turtle board. I'm planning to have an ESP, which will host a web server and the entire visual programming stack within a couple of megabytes. So then you just connect to your battery pack powered turtle, and on your phone or laptop, whatever web connected device, you build the code for FT40, RT90, these things, to have like a logo turtle which moves around. That's a future plan. So.
Can we resume the questions after the other talks? Okay, while the slides are getting set up, we have Aditi now who will talk to us about how API dispatching is being used to improve performance in Python libraries.
Yeah, hello. Yeah, so I'm just going to start talking. So I'm going to just talk about dispatching approaches in different scientific Python projects. And so dispatching, you must have heard it like your package has been dispatched, your Amazon package, and it goes, basically means it is going from location A to location B. And how does it go from location A to location B? By some address information. So in programming also, dispatching is kind of in a similar way, and but instead of going from location A to location B, it goes from library A to library B, the function call. And how it reaches the library B is via like maybe some information in the function call itself, or the type of arguments that you are passing in. So like this. But why do we do it? So maybe to improve performance, like library B has better performance, and maybe it is like compatible with better types. And so now here's an example. So here's a library, and it has basically a add function. So like calling a library, another library, would just mean like importing it and calling it. So I have like different if else conditions for library b1, b2, b, and you also have to like modify the function call for each of the library b1, b2, b3. And but this is not a very nice way to do it. So maybe we can generalize it a bit. Like you can see there are like these few steps that are getting repeated again and again. Like you get the library name, and then you import it, and then you convert the argument. Like maybe library b1 only takes z when it's float type, and then you find that add function inside library b1 and call it. So here, like instead of like library A finding the function, I'm just saying give me a namespace of all the function that you support library b1, and I will just call the add function. And instead of library A converting the arguments, I'm saying you give me the convert argument function for all of your functions. And instead of importing, I'm using this import dunder method. And now a consequence is that like all the if else code blocks have become quite general, so I can just use a single if else, and here you can see like I've delegated these last two steps to library B1, and if library B1 does not want to do it, then of course like you would have to hard code it. But like maybe I can squeeze it a bit more by using a decorator. So I have just put this code into a decorator, and now you just have to put like your decorator on all the functions in library A to make them like dispatch to another library. So this is like basically dispatching, like you user calls the add function and dispatch will just dispatch to whatever implementation the user has wants to run. So now we are going to see example of network X, NumPy, and then like a little bit of scikit-image and Spatch, how dispatching is implemented in those projects. So in network X, there are networks that we analyze. Networks are also called graphs, and they have nodes, and if two nodes have some sort of relationship between them, we put an edge between them. So these are not like formal steps, these are just my observations that I have made in dispatching in scientific Python ecosystem. So this is our demo, you can like go and see it. So it basically like with normal network X graph it takes around 80 seconds, and with cuGraph it's like 3 seconds, so it's quite fast. The between centrality algorithm, these are like how we take the backend, like which backend to dispatch. So you can take this cu graph, which is like cuGraph object, and if you check the network X underscore backend, it just contains a string called cusim. So we know that we have to sorry, cuGraphs, not cusim. So we just know that we have to dispatch to the NX cuGraph backend, or you can pass in directly as a backend keyword argument the backend name, or you can pass in as a global configuration, and backend priority is basically if cuGraph does not work, go to graph plus backend then parallel. And you can also set a environment variable, and you can see like two types of dispatching, like type based and name based. So type based means we are dispatching based on the type of the input argument, and name based is we are dispatching based on the name that you have given us. And entry points helps us to match create a mapping between the name of the backend and the namespace of all the supported functions by that backend. So entry points are basically primarily used to like extend the functionality. So like the functionality of a vacuum cleaner is to clean, and you can just change the nozzle if you like want to clean the corners or something. But dispatching is like you can change the whole machinery inside the vacuum cleaner. Like we are allowing you to like change the whole implementation. So this is how entry points look inside network X. We just have to like call this entry point function, and it groups all the packages which have this entry point with the group name network x.backend. So like parallel cuGraph, and so you can see this mapping between like the name of the backend, and this backend interface is nothing but a namespace of all the supported functions, and also like the convert functions, like function to convert a network X graph to a NX parallel graph, and NX parallel graph to a network X graph. So, and this is how it looks in the NX parallel side, like how you define an entry point to let the main network X library that NX parallel is a backend. And these are some more features. So in NumPy, we don't do the conversion step because in arrays conversion is a bit complicated. So in arrays you would mostly see type based dispatching and not backend name based. So here we have like we call a function, we pass a CuPy array in a np.mean function, and what it does is that it takes that CuPy array and tries to find this array function method, and that this gender method automatically calls the CuPy implementation of the mean function. So but what is happening here, so it just basically takes the function name like np.mean and the type the CuPy array, and it can also be like some functions take like multiple arrays and all the other keyword arguments, and then we just see if it's a supported function and see if all the types are of the appropriate type, and if they are, then CuPy NumPy runs its own mean implementation, but one drawback is that there's no fallback in NetworkX. Fallback in the sense, if KuttyPy does not implement np.mean, then it will not fall back to native NumPy's implementation, but in NetworkX it does fall back to, like, if backend does not implement a function, it will go to the main library's implementation. And yeah, it evolved from array ufuncs, and in scikit image the challenge is that the main image object is a NumPy array, so ideally you would think that we should adopt array API standards, like array API standards Pradyot will talk about in next talk. Like, this array function was not like suitable for all kinds of arrays out there, so array API standards was introduced, and also like scikit image is Python heavy, so it's hard to adopt it, so we use entry points instead. And the goal is to like make it look like type-based dispatching, but under the hood have entry point based, and currently we don't have any. Like, it's a very basic implementation, and one possible solution is Spatch, which is short for Scientific Python Dispatch, that we are working on, which like potentially other scientific Python projects could also use to introduce this dispatching kind of mechanism. And this is a summary. Like, in NetworkX you either get a NX parallel graph, or a graph plus graph, or a NX2 graph, and then from the function checks the dispatchable decorator, checks this NetworkX backend, and that's how we get the backend name, or we can get it from the user also, and then we load the entry point name and the backend namespace corresponding to that backend name, and from these two functions we get the output. And in NumPy we take the dask array or a KuttyPy array, and then we run this array function, and that runs the KuttyPy implementation or a dask array implementation. And next talk is this, and here are a few links if you want to read more, and I am around, so thank you.
So as Aditi hinted, we will have Pradyot now talking about the array API standards.
Hi everyone. In this really small talk, I'll be talking really briefly about array API standards and how it fits into the array scientific Python ecosystem, and why is it useful, and how it deals with when we are working with multiple arrays. So a bit about me. I'm currently a software engineer at PyHex Labs, and I'm also an open source contributor at the PyData sparse community. I've also worked with the PyBAM community, and yeah, that is about something that I like doing in my free time. So a bit about scientific Python. Well, it deals with the Python libraries that deals with the scientific and technical computing. So anything like NumPy, SciPy, Matplotlib, or all the scientific Python projects that we know are part of the scientific Python ecosystem. And what it aims to is to provide a common API spec and standards and interoperability and long-term sustainability of the project, so that it's maintainable and maintained for a really long time. So as we all know, there are a lot of different array libraries like NumPy that is used for different purposes. Like PyData sparse is used for mostly for the sparse matrix calculation. KuttyPy is basically NumPy that is used for GPU, and then we have NumPy for almost everything, all kind of numerical calculations. So yeah. Since we have a lot of different array libraries, we can roughly divide them into two sections, the array producer library and the array consumer library. So the libraries like NumPy, KuttyPy, JAX are the part of array producer libraries, and the libraries like SciPy, scikit-learn are part of the consumer libraries. So what exactly are the producer libraries? Well, as the name suggests, it introduces a new kind of library or a new kind of array to the ecosystem, which is tailored for specific use case. It might be based upon already existing ones, but ultimately it gives us a new array. Yeah, so NumPy, SciPy are all part of the producer library ecosystem. And then we have a consumer library, which just operates on the array-like objects and not necessarily introducing a new array, but work on the already existing ones. And they can basically consume the producer library arrays. We have a really small example of how SciPy is just basically using NumPy under the hood. So A is basically a NumPy array, and we pass it and find the eigenvalues in eigenvector using the SciPy function. And if you try to find the type of the eigenvector, it is basically a NumPy array. So what exactly is the problem here? Well, you can figure it out. It's basically the limitations of the producer libraries are also the limitations of the consumer library. So one famous example is the scikit-learn project. Well, scikit-learn was basically, and a lot of the libraries back in time were basically built using having a NumPy as a backend. So they were really restrictive because NumPy is CPU only. So scikit-learn as a project had very trouble switching to like GPU executions and stuff. So the solution is actually pretty simple. If we had a way somehow to support multiple producer libraries as a backend and for one consumer library. So here the array API standards comes into picture. Array API standards basically a set of agreed upon functions and behaviors for an array. And it provides consistent APIs and array operations across different Python libraries. So if your code is like array API standard compliant, then basically you can get a backend agnostic code, and you don't have to think about the backend implementation, and you can just write using the core logic of stuff. So what does array API standard mean in terms of the producer library? Well, you get a bunch of defined mathematical functions that are consistent across arrays, like multiple arrays. And yeah, like log, expression, maximum, minimum, which is required by all the matrices and stuff for the calculation. You get everything as a part of the standard. In terms of consumer library, you basically get a backend agnostic ecosystem where you don't have to think about the backend of the execution part, and the array API standard takes care of that. It's also easily maintained, and it provides a simplified user experience. Yeah, so it's a small example of how SciPy and CuPy can work together. Well, X is basically a CuPy array, and Y we try to find the fast Fourier transform of X using a SciPy function. And yeah, if you try to print the value of Y, it's a CuPy array. So what it basically does is dynamically switch to the CuPy function of the fast Fourier transform, and that is how it does the calculation. Yeah, so this was a very brief talk on the array API standards. If you have any questions.
Okay, we'll move on to the next talk. So we'll now hear some more about arrays from Sanket, who'll tell us what's new with Zarr. Sanket is a long-time maintainer of Zarr and a significant contributor to the scientific Python ecosystem. And he's also on the NumFocus steering committee.
Hello everyone. Hello. Hello. Yeah. So I'm Sanket Verma, and I'll be talking about Zarr. We are here at IndiaFOSS 25 in Bangalore, Karnataka, and this is 21st September. So before I start, may I get a show of hands how many people know and use Zarr? Okay. So yeah, I'm Sanket Verma. I wear many hats in the open source ecosystem. This is my website if you want to check more about me. Apart from all the other things, I have been maintaining Zarr for the last 3 years or something. These are the slides for the talk, so if you want to follow along, I'll leave this QR code for a few seconds. And there's also a link at the bottom. So this is a brief outline what I'll be talking about. So basically what is Zarr, the basics, and what's new in the Zarr Python 3 and how you can get involved. And if we have time, we'll go to the Q&As. So basically Zarr is a community project that develops specifications and softwares for storing n-dimensional arrays. And it was created by Alistair Miles, who is a genome scientist. And at the time he was working with malaria mosquitoes. And at the time there was like no, this is like back in 2016, like, you know, a decade ago, and there was like no library who could, or specification who could handle the massive data sets which are coming out of like malaria genomes. And it has evolved since then. Zarr is actually adopted in like many scientific domains, which are including but not limited to geospatial, bioimaging, data science, physics, and everything. So I'll just briefly explain like how Zarr works. So these are like arrays, you know, we have different like shapes of arrays like 1D, 2D, 3D, and ND. If you have like a small array which you can easily fit into your memory, you can do operations on it, then it's completely fine, right? But what if the data is too big to fit in your memory? Like, you know, it'll crash, you'll get runtime memory errors, and you know, your laptop will crash. So this is where basically Zarr kicks in, and it helps divide your big array into like small chunks, and you compress those each chunk and store them into your into your secondary memory. And the retrieval works in a way that only the selected chunks or the subset of chunks will be loaded into your memory, not the entire array. So and every chunk is basically assigned a key. And if you imagine like a key value store, the key is actually the address of that small chunk, and the value is actually the data in binary format stored into that chunk. This is just like a graph. This is just like a slide which shows like how it works in the Python land, like the mutable mapping. So Zarr is actually a specification. So for the uninitiated in the audience, specification is basically a technical document which lays out the rules how the format should work. Currently we are at version 3, and this is the link for the spec if you are feeling like brave enough to like read the whole spec. Yeah, as I said, like it defines the metadata scheme, how the chunking would work, how the hierarchies are basically managed, the attributes which are basically custom attributes to add to the data, and all the other things. The implementation exists in like various languages like Python, C++, Rust, R, Julia, and everything. And Python is kind of like the more used and more famous implementation because of the community and everything. Bringing to which I'll talk about the Zarr Python 3. So we have been like working for the last, I think, 2.5 years, and just this January we released Zarr Python 3. So there's a lot of new things in the new library. If you want to like install, you can do the pip upgrade, and or via conda channels. I'll briefly touch upon like what's new in Zarr Python 3 and Zarr Spec 3. So basically, the version 2 spec was written alongside with Zarr Python. So it tied very closely to the NumPy fundamentals, and which was kind of like getting irritable and, you know, like troublesome for the other language implementations to work on. So the aim for the version 3 spec was to be as lean as possible and interoperable with other languages. And so also the version 2 spec was kind of like a test field area to figure out the issues and the challenges when you're working with like high latency storage like cloud objects, which is AWS and all this stuff. And we use that learnings from the version 2 and kind of like design the spec in a way that it handles the high latency storage. And the most important part was the extensibility, which is the spec has been reduced to a minimal required things, and it adds like mechanisms to add like custom attributes or custom data types or custom chunking schemes to the Zarr v3 spec. So it allows various domain specific applications to add like multiple features which is suitable for their domain. So these are the 3 points which kind of like we have keep in mind when developing the version 3 spec. This is basically a diagram which kind of shows like what's the difference between the array in version 2 and version 3. On the left hand side, you see the version 2. So you can see the Z array is like a metadata file at the top of the array, which contains the information about what is inside the array, what's the size, what the data type is, and all that stuff. And Z address is like the custom attribute. So let's just say you created the array, which is kind of like a data coming out of like a Large Hadron Collider, and it contains like various information. And in the earlier version 2, like it was like the metadata files were kind of like separate. In the version 2, we have consolidated into like Zarr.json, which is more acceptable form when you're working with like array libraries. And the array is also kind of like chunked in like various in a different manner and stored in different manner. And similarly for groups, like you can see the groups are also like shaped in a different categorized in a different manner, and the way you access the groups is also changed, because keeping in mind like when you work with high latency storage, how it will work. We have introduced a new storage class, which is the abstract base class. This is a very exciting thing because we have replaced the mutable mapping class in the Zarr Python and allow a new base class. And it kind of like adds an entry point mechanism to add your own custom stores. And we have removed all the exquisite stores from the Zarr Python to decrease the store bloating. So earlier there were like many stores like SQLite, MongoDB, Redis, and whatnot. And we wanted to make the spec as well as the implementation of Zarr Python like as lean as possible with like minimal functionality. And the Zarr Python library implements local store, zip store, and FS store, which is the last store is for the remote reading and writing. And if you want to work on like add your custom stores, if you want to read via like MongoDB or Redis, you can add these stores as well. We added like custom codecs via entry point mechanism. So this is also highlighting the extensibility part in the V3 spec I mentioned earlier. And we have removed a lot of codecs from the Zarr Python and included only the BLOSK, Z standard, and gzip compressor only. And if you want to add like new codecs to the existing library, this works as same as the storage classes. These are like some of the logos of the adopters who are using Zarr in their institutions, and they have been storing massive data sets in clouds. I think the largest data set which I have seen in Zarr is probably around like 50 petabytes or something, which is stored in like Amazon AWS, which is like a climate data set of how ocean currents are basically working. I think this is like, there are a couple of more logos here which are missing here, but yeah, you can check out this link and this page is updated. We have meetings almost every week. So yeah, if you are looking to join the community meetings, office hours, I do host office hours if you're interested to learn more about the project. And if you're coming from a scientific Python background or science background and want to use store your data set into Zarr, yeah, I'm happy to chat with you. There are dev meetings as well. Here's a link for the calendar where you can see that. And I think that's it. Thank you. Take questions if anyone wants to.
Can we do questions later?
Okay, sure. Thank you.
You can meet Sanket outside. We have a break coming up soon. So we'll have a slight change of pace now. We have Pradeep talking about the role of FOSS in assessing the state of India's birds. Pradeep is a wildlife biologist working on applied ecological and conservation science issues in the Indian context.
Good morning. So just before I start, a quick show of hands. How many of you watch birds for fun or as a hobby? Great. That's a lot of us. I was just wondering, even as of this morning, how I'll introduce this talk, because this is about very different things compared to what we've heard about this morning. This is not about anything that you could do a pip install birds with. A friend of mine at breakfast told me if I said that, people will know what I'm not talking about today. This is about birds that we see around us, lots of them. India is lucky to have over 1,000 species of birds to be found here. So at State of India's Birds is a partnership of many individuals and 14 different organizations. We've all come together to assess the state of India's birds, right? So what we set out to do is provide the best current knowledge on the status and conservation of India's birds. We do that by curating, analyzing, and synthesizing available information and producing a variety of knowledge products that are used by a wide variety of folks in various walks of life in the country. All the knowledge products we produce are freely available, and all our science and results are published publicly and freely. The main flagship knowledge product we produce is a comprehensive report that we call the State of India's Birds reports. There have been 2 editions so far. The first one was in 2020. The most recent one was in 2023. So perhaps the most central thing, the key thing that we rely on to build our work on is a large corpus of publicly available citizen science data. So birders, like many of you here, who are, I'm guessing many of you are familiar with the eBird platform. eBird is a corpus of data where birders submit their logs of birding activity, observations of birds, and so on. In India, as you can see in the GIF there, somewhere around 2013, 2014, activity on eBird in India picked up, and it's just gone through the roof in the last year. There are nearly 60,000 people on the platform now, logging 3.8 million hours of birding. There are upwards of 70 million observations on the platform, 700,000, more than 700,000 locations these logs are submitted from, and this covers 1,379 species of birds across the country. Yeah, so that's the massive growth of observations, the data corpus that we can build on. So at the partnership, we all got together and tried to work with it to see what sense we can make of about the status and trends of birds. But the one thing about eBird data or many citizen science data like that is it's often opportunistic hobbyist birders and hobbyist citizen scientists submitting observations. So when scientists come to apply rigorous statistical approaches and frameworks and methods to completely unstructured data like that, you have to be a little bit careful in like dealing with the data and making sure it's properly cleaned and so on. And then the statistical modeling approaches can be applied. So all of this is plenty of processing and analysis, statistical analysis. So what we do is we build all our analysis on R. We use many very powerful, what we found as being very powerful statistical and data processing libraries in R. For example, the entire tidyverse universe for data cleaning, statistical modeling using LME4 and unmarked, and parallelization and visualization also using R packages. So that's just a schematic of the processing involved. So we start from the eBird data, but after some processing, there are 2 different branches. Each one branch produces the trends of the abundance of birds as they are observed out there, and also the other branch produces a distribution range map for each species. So for each species, we are able to produce these trends and distributions, and then both those are put together along with a bunch of other metadata, so to speak, that are known about birds in India, and we put all of this together and come up with what we think is the conservation status for each species. So that's, and all of this scientific work, whether it is methods or results, they're all public. All the code is public. It's archived in a archiving platform, Zenodo. Our GitHub account has all the code involved. All the results also, like I said, for every species, we're able to produce the trends and distribution. So there we have a website where all of that is available for easy consumption. If you I don't know if you can see my mouse, but this little card there is what a page for a particular species looks like. So the distribution range map for all of India, the trends over many years, starting from before 2000 to now, that time series, and all the associated information. And that's the website. If you ever want to go take a look, you're most welcome. In addition to just that website, we also have a web tool, which we call Mina. Mina stands for monitor your neighborhood avifauna thanks to ChatGPT. But also, I mean, it's really good because it's also a very common and very widely loved bird that we see out there everywhere. So this is a web tool where you can use this tool to build on the data corpus that we start from eBird data, we do some pre-processing and cleaning and so on, and make it a little bit more tight and rigorous. And on that corpus of several tens of millions of rows of observations, this web tool is built. And using this, you can build localized regional reports on the broad picture of bird life in that area. So for example, species details, IUCN status, seasonality, most common species, endemic species, all of these things. And even, I mean, we already have heard about these reports being used by many advocacy groups, many people in the forest department, many places where citizen groups want to go, or advocate for a particular patch of some natural area being protected, or some planning around there, and so on. So these reports are used to give a summary of what bird life is there in those areas. So this is, so the SOIB, what State of India's birds does is captured in this schematic, where essentially we start from, we stand on the shoulders of work that bird watchers put in just by going out there and observing and logging their observations onto this eBird portal. eBird, generously, the terms of all the data is once you upload it in there, the entire corpus is public. So we are able to benefit from the entire corpus of nearly 100 million rows of data for India. We use that to come up with the State of India's birds, the analysis for each and every species. We have from 1,300 and odd species. After doing statistical analysis and seeing how well the statistics works out and so on, more than 900 species we have trends and distribution ranges for in that website. So 940 or something, if I remember right. So that comes out of the State of India's birds. Then we have the Mina tool through which you can build regional reports. And using that, hopefully people are using this out there and they see that them contributing to eBird is going around and coming back to them being able to use it to understand more about the regional bird life and so on. That's where State of India's bird sees itself. One of the key challenges at a purely practical level has been that the data corpus, like I said, has been growing very fast in the past decade. When we made our first report in 2020, the corpus was 10 million rows. All the analysis for nearly 1,000 species ran on my friend, one colleague, his one laptop, took care of all the analysis. When we got to 2023, that corpus had grown to 30 million rows of data. Already, the compute resources we had across the partnership was creaking a little bit, and then it's just been really hard as the data corpus has been growing. Now we are sitting on more than 70 million rows of data, and in a couple of years, if we want to do another report, we may be looking at nearly 100 million rows of observations to deal with. So just the computation, just to get all of this analysis through and get the results is something that we were not used to. And then some of us, we learned, I mean, we all had FOSS and all of these things in the back of our mind, but then we realized that's essential, that we simply don't have the skills to be able to do this ourselves. So we now speak to folks like you in the room. Some of you have been generous and very kind, and you've come along and helped us. And now we are actually within striking distance of being able to do this analysis, not just now, but into the future as well. Even, we are future ready. We will be able to do this analysis, even if it crosses 100 million and so on. It's highly scalable. So the scalability and affordability of this kind of analysis to enable work of State of India's birds is just central. All of us are non-profit organizations, government institutions in the partnership. We are not software people. We know some science. We are ecologists. We know some conservation science. But people like you are really crucial in order to be able to help us do what we do. So thanks a lot for all the FOSS work that you all do. Some of it does come around. And so, yeah, the takeaway is FOSS is key even to enable work that even folks like us do. Thanks a lot.
We'll now move to our next talk. Arjun will talk about CAD and GIS in JupyterLab. Arjun is a mentor at PyBAMM project under NumFocus and a contributor to the Jupyter ecosystem on projects such as Jupyter CAD, Jupyter GIS, IPy Leaflet, and much more.
Hello. Thank you all for attending this talk. So I'm Arjun. I would be talking about collaborative and reproducible CAD and GIS in JupyterLab and Jupyter Lite. So I recently graduated this year only, and I am a scientific software developer at Quantstack now. So let's first discuss the problem. So sharing CAD and GIS workflows is quite painful. Like when you try to share a QGIS file and the other person might have a different version. Your QGIS file, like there is 90% chance that your QGIS file would not open and would just throw an error that you are not, you have not seen before, and you are just lost. That how do you go ahead? So there is very little reproducibility to no reproducibility, and there is complex UIs. There are a lot of buttons when we talk about either FreeCAD or either QGIS. Like there are 3 rows of buttons and I guess 30 or 40 buttons in the UI, which is quite complex and not beginner friendly at all. And like when we talk about these desktop tools, while installing, they can throw very weird errors that like could not install. You would have to just re-download and try to install it again, and they are quite huge, and it can take hours to even download the binaries of these applications. But when it comes to browser native applications, they are like just throw a link and open in the browser, clean UI, collaborative and reproducible. So here comes Jupyter in the picture. So what we do is that we are trying to replicate the experience of QGIS and FreeCAD inside the browser. So Jupyter CAD and Jupyter GIS are CAD and spatial computing applications built in Jupyter ecosystem inside the browser only. It is also powered by WebAssembly and Jupyter CRTTs, which enables a real-time collaboration. Like you can be sitting anywhere in the world and you can still collaborate with a colleague that you're working with, like Google Docs. So why does it matter? Why we started to build Jupyter GIS and Jupyter CAD in the first place? Because like science should be shareable, transparent, and reproducible at any point of time. But these desktop workflows are quite fragile and based on the versions and installs and lot of things going on, and you do not know like when you do something in these desktop heavy apps, you do not know what's going in the backend, and if you want to audit these steps, if you want to maybe customize the process a little, you cannot. You would have to go a little much deeper and try to understand what's going on first in the application, and maybe you would just be lost for a while. And when it comes to browser native applications, when it comes to Jupyter specifically, your code is in front of you. You can modify the code and you can just play with it. So there is why browser plus WebAssembly? Because it provides a universal runtime. You do not need to install again and again. You just open a URL in your browser and everything works on the fly. And it is beyond CAD and GIS. You can do physics, you can do genomics, like climate analysis and all, and it is language agnostic. So you can be doing CAD or GIS, or you can side by side you can be analyzing the data with Python or R, Julia, or you can be processing it with processing the data with any of the language. It is like you can totally connect with any language, and it is totally language agnostic and reproducible workflows because they are notebooks. So yeah, let's first talk about JupyterCAD. I hope it's nicely visible. So this is JupyterCAD. Like it is, I have embedded the Jupyter Lite, which is a static application of JupyterCAD over here, and you can see it working over here. And now we would see what more we can do with JupyterCAD. So about JupyterCAD, it is browser native 3D modeling for JupyterLab and Jupyter Lite, and it is built on OpenCascade, which is a 3D engine, which does all the processing that goes on in the backend, and it is parametric sketch-driven design and integrates with Python code cells as well. So you can create custom sketches like this, and like if I want to create a star, I would just do something like this. I would not create the full star, I would just create this 2 lines and save it. I have this, and I would now extrude it. Maybe give it in the 5 and color red. Oof. Yeah, as you can see, it has been extruded. It does not look too good, but maybe the next one would be. So you can do Boolean operations and other geometrical operations that you do in FreeCAD or any other CAD application. So if I would add a sphere, and I would like to cut my box with a sphere, so I would just select both of these two and select the option to cut. I would select base as box and tool as sphere and would submit it, and now my box has been is cut with the sphere. So you can notice the void that's been created over here. And you can do union, you can do intersection, and similarly you can do fillets and chamfer as well. So I would show you how you can do fillets. So I would select the edges of the box, and I would like to make them smoother. So yeah, as you can see, the edges are now smoother. Let's see next. It is a nice example. A box has been cut 8 times maybe with a sphere, and now it looks good. And you can do a lot more. I'm not a CAD expert, that's why I'm just showing very basic things. But yeah, there is this complex model. There we support multiple views. So there is this exploded view. We have this slider. When we enable the button, we have this slider visible. So we can select this and set the exploding factor, and you can see what's going on in your model. It's like every part of the model is has a distance, like is now separated, and you can see what's going on and how and yeah, we also have clip plane. You can it like plays with the visibility of the model when you move this plane. And we also have the wireframe view. If I would just as you can see, if I enable it, I can see the wireframe of the model. And yeah, so we also support transform control. So as you can see, the pointer of this point is quite sharp, so I would not like to carry it in my bag, so I would just maybe remove it like this, and now I have a detachable screwdriver. And Python API, it also supports, JupyterCAD also supports Python API, so I would just paste some code, and now you can see the gear has been created. And you can do a lot more with the Python code. With Python you can script models, and you can like this gear you can create advanced models as well. And we also support our widget in rendering inside the notebook only. So as you can see, this model is we are working inside a notebook this time, and we are doing everything inside the notebook, and we have some code because we have Python API, so we can interact with the models and set the colors and all the properties and do all the operations with the correct parameters as well. We also, as I have told before, we also support collaborative editing. So these are two users sitting at separate places. So I move the model because the first user is following the second one. You can see that if I'm moving the model, that one is also moving, and if I'm changing the color is also being changed. And we also have suggestion workflow, like how you review PRs and merge, maybe you accept a suggestion or you reject a suggestion. Similarly, you can do it in JupyterCAD with the models as well. I have created a suggestion for the color of the model, and now if the other user can see that, yeah, someone has created a suggestion, and with the slider he can see that what was the change, and I can accept or reject that suggestion, like how we do in GitHub PRs. And we have because we also are very interoperable, so we support FCSTT file, which is FreeCAD file format. So if you can import a FreeCAD file and you can edit it inside JupyterCAD, and you can create a JupyterCAD file and you can export it as FreeCAD. So both works. You can if you are working with a person who likes FreeCAD, so you can work with him as well very nicely. And we also support STL files, step files, although we do not support modifying them, but because these files are mostly used in 3D printing, so you can also use JupyterCAD for 3D printing as well. And this is a proof of concept that we are working on right now. We also are going to support JupyterCAD MCP in the future, maybe in a couple of weeks. So you can interact with text and your model will be created. As you can see that I have entered a prompt to create a pawn, and it is trying to do that. It is not perfect right now, and I would just tell him to make it better. So it would try to iterate over it and try to make it better. And again, all of this is real-time collaborative, so even the changes that the MCP is making is also reflected to the other user in the real time. It does not look good, but yeah, it is trying to make it better. So yeah, it is not perfect right now, but maybe. Okay, so now let's come to Jupyter GIS. Similarly to JupyterCAD, it is for GIS. Like we are trying to replicate QGIS inside the browser. GIS people, if there is some GIS people over here, they would definitely find it interesting. So about Jupyter GIS, it is a full-feature GIS toolkit inside JupyterLab and also works in JupyterLite. And it supports raster and vector layers, and built on, like the front end is built on open layers, and the backend, like the processing happens on GDAL, compiled in WebAssembly again. So it has vector and raster data support. The green layer in the back you see is a raster layer, and the dots you see, blue dots you see, are vector layers. I can toggle them. I can toggle the raster layer. I can even toggle the base map that I'm using, and I can also change the opacity and all of any of the layer. And now for the vector data, we also support advanced symbology. So if I would right click on the layer, I can edit the symbology. We support canonical, graduated. If I have color attributes in my data, I can support canonical symbology, graduated, categorized, or heat map. So maybe we can try graduated. So it is an earthquake data, so we would represent the magnitude of the data based upon the color. So I would also select the color ramp, maybe autumn, and I have selected 9 classes with equal intervals, and I would classify. So with a range, with equal 9 ranges, it would classify the data, and I would apply it. So now you can see that my data has been like symbolized with graduated symbology, and you also have this nice legends with which you can totally see that what's going on with the representation of your data. And similarly, we also support raster symbology. We have this edit symbology for raster again. We have multi-band symbology. If I would just unset the green band, blue band, and alpha band. No, not alpha band maybe, but so it would maybe should be red. Yes, maybe band 1. Yep, now you can see red. And if I would again select, like just give the band to the green one, so it would be green. And similarly, if I give correct band to each one, it would be black and white, and it would be representing the data that it would want to. We also have single band symbology. We can select the color amp again, and we can apply it. It takes a little bit of time because it is cloud optimized GeoTIFF. So every time it requests to the server, and but yeah, now you can start to see that layer rendering. Maybe the internet is not so fast because that's why it's taking time. But yeah, you can see the symbology being changed for the raster data as well. And we like the layers that we load. We have this nice UI for dynamic management of layers. We can toggle the visibility with this icon, and we can drag and drop the layer to change the arrangement of the layers. Like if I move this down, it would be rendered below the NASA GIBS layer on the map as well. And if I would just move it up, it would be on top of this. And I can also change opacity on the fly for each and every layer. And yeah, we also have this identify panel. So if I select a layer, this I button I can click on this I button and select any attribute on the map. It shows me what's going on with the attribute, the ID, the magnitude, and it supports multiple attributes at one time. So if I have selected this n number of attributes, I can, and if I would want to see what's going on with this one, I can click on this magnify button icon, and it would highlight that feature while zooming on it. And similarly, it works for the polygons and lines as well. So now I would select some countries. So this is Cameroon, and I must have selected a couple of countries. So yeah, if I click on this again, so it would zoom in and show me all the things that the data have. And we are also going to support the attribute table soon, just like QGIS. And we also have this time slider. If I would select the layer and click on this time slider button, and I can just a second click on this time slider button, and maybe I would want 4 frames per second, so I can render the data based upon the time, because this data has time value that when the earthquake was hit. And we also have this nice playback button which automatically moves your slider. And we like, just like Jupyter CAD, we provide interoperability on Jupyter GIS as well. We totally support importing and exporting QGIS files. Like we can create Jupyter GIS file and export it as QGIS file, and we can also import a QGIS file inside Jupyter GIS. So if you would see that I exported earthquake files to QGZ, and in some time you would see a file being created below this file. So this is QGC file, I can open that as well. So it would, like, it is a real QGC file. We are not just renaming it. So we also support annotation and collaboration on Jupyter GIS. if I would change the color ramp, it would also reflect to the other user as well. And if I do anything like move the map as well, it would be visible to the other user as well, and people sitting on different parts of the world can collaborate with them. And again, Jupyter GIS is also notebook compatible. I can load a map, I can do everything that I can do on the Jupyter GIS interface inside the notebook as well. And add a layer, we have this nice Python API, which is still work in progress. Like, it has a lot to improve, but yeah, it supports the basic things. And we also have this processing toolbox like QGIS. So if I would click a layer and select this processing, I can do all of this with the layer. I can maybe create buffer. So I have this earthquake data. I want to see that what is the like. I would see that on the 10-kilometer radius there is a lot of risk. Maybe I'm not sure about the units, but in the 10 units of the center of the earthquake, all the buildings are in risk. So I would maybe buffer it, and in some time, okay, yeah, now you see that the buffer has been created. So I did it a couple of times, so that's why you see 2 layers, but all the things that are in this radius are in the risk. So, and you can do all of these options that are here. You can do dissolve, centroids, convex hull, buffer, bounding box, and everything. And now we use WebAssembly, obviously, PyCRDT and IndexDB Jupyter extensions, and it not just work inside JupyterLab, it works in Jupyter Lite setups. WebAssembly enables install pre-use, and it can also be integrated with Jupyter Hub, Voila, Jupyter Lite, and you can, like, as I have integrated with these slides, I have just used generic iframe of HTML, and it works. So coming to the use cases in science, it can serve the climate and land use analysis. Or I'm just mentioning some of the examples, but there is a lot that you can do. A reproducible workflow, you can share and reproduce the results anywhere. And the technology, in the technology aspect, we use WebAssembly to like, it can, I guess it never goes old, because if you like, if you have compiled something to WebAssembly, it would work after quite some time as well. And enables us to use interactive spatial or CAD apps within like static apps within the slides, within without any heavy backend. Yeah, like, especially CAD is closely related to engineering. So yeah, and Jupyter is already being used so much in education and in schools. So with the help of Jupyter CAD and Jupyter GIS, it also enables the accessibility for the students and for the teachers as well to easily provide the education about Jupyter CAD and Jupyter GIS. When I was a kid, I did not have enough hardware resources, so I was always short of being able to try these type of applications, but now we can. So if you want to contribute to the project, all types of contributions are welcome. Bug fixes, feedbacks, and everything. And these are the some links. And we have bi-weekly hackathon organized every 2 weeks, and we have weekly catch-ups for the GeoJupyter community. So feel free to join, and feel free to try to like, we would really welcome you in the community. Yeah, thank you. You can try both of these applications live, and yeah, thank you.
We have time for a few questions.
So like the simulations or like animations that you created from CAD and GIS, if we import it on our computer, like, will they be really big files or?
No. So these both of these Jupyter CAD and Jupyter GIS files are purely JSON format. So like, even you can read it without with human eye as well. You can see what's going on inside a file. Even if there is a, like, I showed you a big table in the start when I was showing you the JupyterCAD demo. So it would be like, I'm not sure about the size, but it would be very small, very small. Like the initial file that can you hear me?
Yes, yes.
The initial files that I showed you were like would be about would be less than 200 lines of JSON. So
Thank
it's
you.
quite lightweight.
Thank
Yeah, so we have been talking internally about integration with cesium because there is something like open layer cesium, but we are not sure about if we would, if we do have enough bandwidth and enough resources to do that right now. But yeah, we do have plans to do that as well. No, everything like so we create things on plugin based most of the time. So uh, like if there's something like if we would not definitely like to make open layer cesium required for the application. We would like to it to be like an option if you like to see that if you like to see your app map in 3D. So you can maybe enable it, or you can we can, like, I am not sure, but maybe we can also create it as a separate extension altogether, so that you can just plug in and play with it as well.
Do we have more questions? Any more questions? Okay. We'll break now for 15 minutes, and we'll start again with the next session at 11:45. Thank you.
Where is my screen?
Which one do you need?
Is the Wi-Fi okay? Should I try with the hotspot? It's fine. It's okay. I can. The signal seems fine. It's okay. Just come.
Hi, everyone. Welcome back to the FOSS and Science Devroom. We will now hear about the Core Stack Open Source Initiative from Professor Aaditeshwar. Professor Adi is from the Department of Computer Science and Engineering at IIT Delhi, where he runs the Appropriate Computing Technologies for Development Research Group.
Great. Thanks. Yeah, this works. Great. I'm very excited to be here, folks. It's my first time to a FOSS conference. And I've been loving all the talks. Really great work, all of you. Great. So let me talk about this new project that we've been working on for a couple of years. Yeah. And as you can see, it's with a large network of people. So what do we do? So first of all, a lot of it is about how do we use computer science to make an real impact on the ground. The first step over here is really to understand, right, what are the problems that we're trying to solve, right? And here, all this problem discovery really happens from the community. So we spend a lot of time in the field doing forest walks and things like that. And this is where we start discovering, right, what are the kind of problems that communities are troubled with, or when they're trying to do environment planning, natural resource management planning, what are the kind of questions that they're facing? Yeah. So for example, right, this is a unlined farm pond, which means that when water collects over here from the rain, it percolates into the ground and it enriches all the soil moisture. But this is a lined farm pond, which has a very different purpose. Here you pump water from the ground and you store it. So this one is really good for rain-fed agriculture, but this one also leads to groundwater depletion, right? And it's more used in more commercialization of agriculture. How many of these can the landscape support, right? What's the carrying capacity? Those are the kind of questions that come up, right? Likewise, right, so landscapes like this where, you know, there's forests and there's farms in the foothills, these are awesome because the runoff, when rain falls and the runoff flows into the farms, that's very nutrient rich. A lot of soil organic carbon and other things come from here. And likewise, right, in different kinds of terrain, there are different traditional water structures that have been there. But now, because groundwater and such things are more easily available, many of these traditional systems are not being maintained. So all these channels are blocked and so on. So how do you figure out, right? How do you, in some sense, debug the landscape? And then, of course, there's more socio-economic things, right? People want to move out from the villages. They want to get an exciting life. They have aspirations. But how do you manage all of those things, right? So that's really what the core stack is meant for, that how do we build tools and systems and use data and everything, put those in the hands of the community, right? So that they can really think about what kind of destinies they want to pursue for themselves, yeah? And now the challenges, right? So when we think about a landscape, what are the challenges over here? Now this, of course, right, all of us understand, right, that we have been living in a very interconnected web, where water, soil, biodiversity, all these things, right, have feedback loops with each other. And we have royally, totally messed it all up. And what are some of the big issues, right, because of which actually the fault lines are very common. Yeah, there's a disconnect between individual good and common good, a lot of, right, desire to move fast and so on. So through all of these field immersions and everything, we found that there are three things that we really need to work on where technology can play a role, right? So one is around making sure that marginalized groups, right? Why do people, why is there so much focus on individual good? Yeah. A lot of it is because of stemming from inequality. And why is there so much inequality? Why isn't it not going away, even though we have affirmative action and so many things, right? It's largely because the power structures are still very imbalanced. And right, so how do we make sure that some of these structures like farm ponds and other things, right, that marginalized groups are demanding, that lower caste communities, tribal communities are demanding, they actually get those? Because unfortunately what happens is that there is a lot of elite capture, corruption, larger farmers and that communities, right, which are more politically connected, they end up getting many of these benefits. So there's a lot of need for making systems that when such communities are demanding such structures, and government schemes are meant to support that. Yeah, the government schemes are also structured to work in this bottom-up manner, right? But many of these things, you know, go haywire. So, right, so we need systems that can, technology that can improve transparency, right? Maintain accountability. then also use science and data and so on so that the planning is more informed, right? It's more technically and scientifically sound, right? Like for example, how much groundwater pumping can a particular landscape support, right? So those things can be determined through different hydrological modelings and so on. Yeah. And finally, the communities also need to have some sort of a collectivization happening, right? So that everybody has a shared understanding and they can align that, how much of sugarcane can be planted in a particular area, right? For example, right? So that, right, just getting everyone to come on the same page, right? This is again one of the places where we think data can help, right? Where if communities see visualizations, they sit together and they discuss some of these things, right? They see this is what's happening in our village, what's happening in the neighboring village, right? They can contrast and compare these things. That's where again we feel that a wider perspective can be built, right? So that's really the background, right? Now, how are we going about solving all of it? So we're building this core stack, which we view as a digital public infrastructure, and we are doing it at a bunch of different layers. Yeah. So at the base, for any landscape, we are bringing a lot of these different data sets together. How is land use and land cover changing over time? Which areas are getting deforested? Where is forest canopy cover reducing? Yeah. So a lot of these models, now this is where the science comes in. Researchers have built these things. Many of my own students have been working on such things as part of their PhD and master's research. So they build these models, and then we take them and we're using them in the core stack. Yeah. So how do we use machine learning on satellite data and different kinds of hydrological modeling and so on, climate models, climate projections, to get all this data together? Yeah. On that, we can then compute analytics, right? That for a given spatial unit, like a village or a panchayat, we're able to compute a lot of these different indicators, yeah, of how things are changing. And just for perspective, right? When we started this work, we did some, we tried to understand, right, how many such indicators are relevant when it comes to describing a landscape. Because you need to understand how is agriculture changing, how is biodiversity changing, surface water, groundwater, forest, right? So many things. So we went to a whole bunch of like different areas, right, from Rajasthan to Odisha, Jharkhand, Bihar, Raichur. And overall, we built a set of, again, it's not complete, but 81 sort of broad variables. Out of those 81, over 2 years, we've just been able to, with a lot of hard work and a large team that we've been working with of students and computer scientists, we've hardly gotten to about 22. Yeah. So there's a long gap. And that is really where I hope many of you can also come together and join us in this. Yeah. Because you need all that complexity to be able to really understand and figure out, right, what are the trade-offs, right? You increase one thing, how does it start affecting something else? Yeah. And then I'll show some of these tools, right? So of course, all of these are also accessible as APIs and everything. So if, for example, anyone wants to build an app where they want to use all these data sets, that's of course there, but we're also building tools on top of it. So I'll show this Know Your Landscape tool very quickly. This tool is meant more for, right, that in a landscape, let's say, an NGO that wants to do some planning. Yeah. So you select a state, district, tehsil, and for this area, we've built automated pipelines. So that pre-compute, it takes us about a day for one tehsil to compute a whole range of these data sets. Yeah. So what you see here is basically these blue boundaries are what are called micro watershed boundaries. This is about 1,000 hectares. So micro watershed is like a saucer, right? It's got edges on one side, and so whatever rain that falls in the saucer that stays over here. It's a bit more complex. It's got one outlet and so on, right? But these are hydrology units that are good for many of these kinds of analysis. Yeah. So what we've done is that for these micro watersheds, right now, if you want to say, show me micro watersheds which are mostly plain or which are a mix of plains and slopes. So what's happening is that at the back, our pipelines ran a terrain computation algorithm, yeah, which uses digital elevation maps. Digital elevation maps tell you that for each pixel, what is the height of the pixel above sea level. On that, we run some algorithms to say, right, which pixels are at the top of, at the bottom of a V-shaped valley, or is it a U-shaped valley, or a flat mountain top, and so on, right? Because all of these different landforms, right, have different ecologies, that ecosystems that will come up, right? So, right, and then this is just a very simple simplification, right? A simple discretization that these areas are mostly yellow, mostly plain, or these areas have a mix of plain and slopes, right? And along with this, then we've got, right, we pulled in rainfall data, runoff, right? So now if you want to see which areas are more drought prone, right, you can do that, yeah? Then likewise, if, right, we identify water bodies remotely, and then for these water bodies, we say, which of these water bodies, how much of them have water throughout the year? How much of them have water only during the monsoons, yeah? So for example, this is a dam, which where you can see it a bit more clearly, right? That some part of the dam has water throughout the year. This one has water during monsoon and post-monsoon. This one only has water during the monsoons, right? So these are, you know, some of the things, and essentially what this then helps us do is that now in a tehsil is a or a sub-district or a block is a good unit, because this is where a lot of planning for government schemes happen, right? And here NGOs are trying to build what are called multi-actor platforms, that they bring in people, NGOs working in different parts, and they also bring in somebody from the forest department, somebody from the agriculture department, somebody from the rural development department, and now they can use this to basically see that, okay, now in these areas which are mostly plain and drought prone, and there is a lot of surface water stress, what kind of program should we do, yeah? So it's very good for that kind of a planning. And likewise, these are detailed reports that for this micro watershed, these reports are generated automatically, that what's the terrain like, some statistics that how much area is plain or how much area is on ridges, what's the land use like, how much area has crops or trees, yeah? Where has there been reduction in tree cover, right? Tree cover which has turned into built up or which has turned into barren, right? So all of these pipelines that we have, similarly cropping intensity, right? Which areas are only able to plant one crop in a year or two crops, right? Is cropping increasing? So all of these pipelines that we have, we generate the outputs year on year, yeah? And then each year we keep refreshing, yeah? So now in one shot, right, similarly surface water, right, rainfall, runoff, evapotranspiration, groundwater, drought occurrences, yeah, which villages intersect with this micro watershed, was the population like. So all of these things are pulled in from different sources, right? This gets pulled in from the census, these things get scraped from the government's NREGA website and so on, right? But again, my broader point is that these are still, you know, just 22 out of those 81, right? There's a lot more that we need. Right, so now one of the things, right, why are we doing all this, right? Because the cool thing is that once you're computationalizing these units, right, now, right, we are in a position that we can start writing these kind of expressions, right? Just logical expressions that in areas where the aquifer is hard rock and the terrain is a mix of plain and slopes and groundwater is steady and double cropping is in some range, right? What should be done, yeah? And here also the idea is not to use experts to like write out these patterns, right? But local NGOs and the communities in these areas, they know what works, right? They know how much, you know, capacity the landscape can sustain. So essentially this can become a way of codifying their local ecological knowledge, yeah? So that's one of the other directions that we're moving in, that based on, and here we're also using LLMs, right? So we basically ingested about 600 NGO reports of different interventions they had done in different areas. And then for those areas, we brought in all of these different variables. And then now we're trying to combine them together, right? That the kind of problems that the LLMs identified, observable symptoms reported by the NGOs, what kind of expressions do they correspond to? So we're trying to do something called symbolic regression, right? Right now, behind this, there's of course, you know, a lot of very interesting computer science to be done, very interesting things that we can borrow from ecologists, Pradeep was talking about some of that, right? Can we also pull in state of the birds information over here, right? So those are things that we should really think about. So there are some cool algorithms, right? Not very complex, right? Like for terrain, it basically sees whether a pixel, right, in its local neighborhood, is it at the top or not, or in a wider neighborhood, where is it, right? So that just helps in this classification. Similarly, for cropping, we use time series of satellite data. Now, the satellites and all this is open data. The satellites revisit the same spot every 5 days. Yeah. So basically, over a year, you can actually build a whole time series of spectral data: red, green, blue, near infrared, shortwave infrared, thermal, lot of such bands, right? And you can then do some simple things, right? You write it as a time series, you then do peak detection in the time series, and you count the number of peaks. So if in a area you're mostly seeing one peak, it's mostly single cropping. If you're seeing 2 peaks, right, there's probably 2 crops being grown. You're seeing 3 peaks, it's 3 crops being grown, or maybe it's a perennial or an annual crop, right? So basically, behind all this, there are we've written all these pipelines, right, for groundwater and lots of interesting things. That how does water flow, right, from one micro watershed? What is the connectivity graph? You can do all this kind of stuff. Essentially, right, you're computationalizing the whole landscape, yeah, and everything in it, right? Water bodies, plantations, farms, right? Ultimately, these are all objects in a landscape, and you're sort of understanding how the landscape is evolving over time. Yeah. So yeah, then so this Noya landscape is more, like I showed, it's more for this broad area level planning. Now, once this area level planning is done and you kind of know what you want to do in an area, we've also built an app called Commons Connect, which is now in the hands of somebody on the ground, like a community volunteer from that area or an NGO, frontline field worker. This actually then allows them to exactly start geotagging, right? That I want to do a farm pond at this point or a check dam at this point. Yeah. And here, again, there are different hydrological models that we can do. That is this actually a good site for a farm pond? Yeah. If a farm pond were done over here, yeah, what will the storage look like? Yeah. For by when is it expected to fill up, and by when, for how long will it stay filled up? Yeah. So these are, other models that can help in decision support. And what this gives ultimately is that after this planning has been done in a village, you can generate what's called a detailed project report. This is now a standard document which can be given to the Gram Sabha. From there it goes to the panchayats. From there it goes into Narega, which is this government scheme that funds many of these assets, right? So this is what brings in that social accountability and transparency as well. Because now in this DPR, we are actually saying that this community has wants this structure, and we're also attaching a score with it, that this is actually the right location for this structure. If a structure were to be built, it will have these kind of benefits, this kind of water availability and so on. Then it becomes very difficult for anybody to deny. Yeah. And that is the whole part about adding transparency and social accountability that I was talking about. Yeah. So there's a lot of, right, very cool modeling stuff that can be done. I'm not going through the details, right? And again, these are landscapes, these are, right, complex systems with a lot of feedback loops, right? So if you, right, create more and more unlined farm ponds, right, ultimately it leads to groundwater depletion, which then reduces their impact on drought, makes areas more vulnerable to drought, right? So it's quite complex, right? And right, there's no end to the research. And the whole idea is that how do we get this research to deployment, right? So there's, right, more detailed, complex modeling that can be done that, right, based on all of these different variables. How much can we forecast that if we do these kind of interventions, is the resilience of this landscape going to improve or not? Yeah. And here we're mostly looking at agriculture, but now you can start imagining, right? You also add a forest model over here. And you start thinking about climate projections, and you start saying that, well, if this forest were to change into some other kind of a forest, then what will be the impact? Yeah, and so on. So there's tons and tons of cool stuff that can be done. Finally, we're also building impact assessment, that if, these things were done, farm ponds and so on, what impact have they had? Yeah. So again, some cool stuff that's right. So the way we do it is that for any farm pond, we look at how the greenness around the farm pond is changing after the intervention year compared to before the intervention year. So what's the difference? And how does it compare to counterfactual locations? Yeah, meaning areas where there is no farm pond but which are very similar to this site. Yeah, in terms of soil, in terms of slope and distance to other water bodies and so on. So these are standard methods to attribute, right? Causal methods to say that the whatever impact we are seeing is actually because of the farm pond. Yeah. So now another right cool stuff that computing all these layers, there are dependencies, right? So you start with some data sets on which you run some algorithms that produces some output, on which you run some other algorithm which produces some output and so on. Yeah. And this we do location by location. And this is also then now to maintain all of it, we are actually moving to using Airflow, where we will represent everything as a DAG, a directed acyclic graph. And then what we can do basically is that if let's say we improve this ML model over here, yeah, then what we want is that everything downstream of it can be automatically recomputed, but it doesn't need to touch any of the other stuff. Yeah. So all dependencies can be then done, right? So we're building these primitives that if you update an algorithm, then or if you update a data set, or if you augment the DAG, you add more stuff to it, right? And then for any data set, you can get the lineage, right? Where did it come from, and so on. Likewise, there's many efficiency improvements. We saw some nice talks, right, about using QPy, and we need exactly those kinds of things because some of these things are actually very compute intensive. So we're also making GPU versions of some of the algorithms. Yeah. Very quickly, right now, while right, so the title that I try to put, right, we saw how we go from community needs to pixels, right, from people to pixels, we're building stuff, but and we're taking it back to the community. And here now the whole idea is that we want it to be very community based, that they are the ones who should be able to do this planning. That's the tools are meant for them. Yeah. So they are the ones who should, and they understand their landscape. They're stewards of their landscapes, right? And these can then be funded through schemes like NREGA or even through carbon credits, right? But how do we fund these stewards, right? So this is where we're also trying to conceive of a model where some fraction of this, yeah, can pay for a reasonable income for these community stewards, right? Because otherwise it is very difficult to retain, right, talent in villages, and talent, right, which can do this kind of technical stuff. So so we're also we've not started on this as yet. This is just theoretical, but we think it can be done. And what this can really enable is, right, so our goal is that can we have 25,000 such stewards across India, one per panchayat, right, that we want to work in, who can do all this. Yeah. So I'll without going into these things, let me just show you, right, that what we're really eager for you guys to help is right. So there's a whole bunch of different things, right? So there's a long list of layers, data sets, right, from agriculture to hydrology, right, and so on, right? These are all things that there's links to papers, right? So many of these papers we want to implement them as pipelines. So we've put up detailed guides on how these pipelines can be built, and we want to have more and more people get interested to work on this. There's a detailed technical manual that we have which outlines, right, all the different data sets that we have so far on forest, welfare, right, different algorithms. There's also APIs that, right, so any of these data sets for a given lat long, you can get the micro watershed. For that, you can get the entire time series like rainfall or other time series. So all these APIs are there. You can embed these maps in your apps or bots or anything, right? Query them through agents. Yeah. So we're really looking forward for more collaboration, more people to join in this effort, which brings, strong science from ecology and hydrology environment of how it should be done, and put it into strong computer science tools, and which can then be taken to the communities. Yeah. I probably went on for too long. Maybe not much time for questions, but yeah. 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 Yeah, that's exactly how it is. Yeah. So actually, it's a whole ecosystem that includes right NGOs at this stage, where they help in problem discovery, field testing, piloting, implementation, and finally taking it to scale up. Who have to right? That's where we get the problems, right? What to solve, and they are the ones who also take it to the ground, right? Where are we sitting in? We are partly sitting on the science side of building these methods, and then partly on the software engineering side of writing the code and everything for it. Yeah, but that's exactly the whole idea, right? Work with partners, NGOs who are on the ground and who can basically build this army of landscape stewards. Yeah. Yeah. Okay. Great. So I'll do.
Next, we have Sagnik telling us how he's formalizing mathematics and scientific computing with an open source theorem prover. Sagnik is a mathematician who works on computational number theory, arithmetic geometry, and algorithmic bioimaging.
No, it's okay. Yeah. Hi. This is Sagnik. So this is probably one of the first times I'm talking in front of an audience which is mostly filled with devs, because usually when I'll be giving such a talk, it will be in front of mathematicians. So it makes my life a bit difficult. And also I have a short amount of time, so I'll try to give you a flavor of what this open source project is, and probably in the end figure out how some of you can contribute as well. So the main thing that I will be talking about is a bit about how do we formalize math, and primarily why it is required at a certain stage. And within the last 3 to 4 years, formalization has come up to be something really important, and it is growing really fast. So this is a point of time where I feel like a lot of open source contributors can join this project as well. So I'll start a bit with this ISOMS 2013 report. So one of the things that we have observed in the mathematical community is that a lot of published results in the area of scientific computing or complex math in general are not easily reproducible. So this does not happen because that mathematicians don't understand each other. It's because things are not well documented how they should be. Like computations, even though we see what the final output is, the process is not as well documented as it should be. So not only that, in a lot of cases, since we as mathematicians prove theorems in natural language, the thought process of proving these theorems are different with respect to different mathematicians. So this results in peer reviewing process to be getting extremely delayed in some cases. So this is an open source project that solves some of these problems. So to figure out how formalization actually came into being, I'll delve a bit into history. So we start with Russell's paradox, which came somewhere in 1900s. So this starts from the basic set theory. So how we define set simply is a collection of objects. So now let us say that a collection is good if it does not contain itself. The premise is very simple. Like if you take a box of oranges, you don't say that the box is contained inside the collection as well. So now consider all kinds of sets which don't have themselves included in it. So this again makes a new collection called R. So if since every collection is defined to be a set, this R should also be a set. And if we proceed like this, so since R does not contain itself, it's again a good set. So, and by definition, R should contain all good sets. So this comes up to be a paradox. So this happens because of a logical fallacy of how do we define sets and how do we define collections. So to solve this, one of the quick fixes that Russell did is to define a theory of types. So in collection of types, what we define are types in different stages. So stage 0 of types will be objects. Then we have set of objects. Then we have set of objects. So if we define things like this, we don't run into complications of creating larger collections and naming them in the same process. This type theory has gotten improved by several other mathematicians in the late 20th century. So this also includes the ZFC theory. So what ZF does is that it creates basic axioms of defining logic in math. And we define what empty sets are, how disjoint sets are, how elements inside sets behave. And we also have something called axiom of choice, and which lets us make sure that even if you have infinitely many sets, it's always possible for us to choose at least one object from each of this set and create a new collection. Like for example, if you have infinitely many number set Si, you can always choose at least one point from each of the sets and create a new collection. So these are some of the axioms that has built early logic theory and type theory in math. They get more improved with Gödel's theorems. So Gödel's theorem mostly defines formal systems of proving logical statements in math and how there is always inconsistency in almost every formal system. So for example, a system, if it's consistent, you can never prove both the statements P and negation of P. So all of this gets also more improved with the introduction of computability and lambda calculus. So Curry and Howard, so how they improved the entire logic system is that they took logic and introduced them to be called as types. They call proofs as programs and formulas also as types. So this is the entire path is slowly going towards using mathematical logic to be very similar to how programming logic works. So nowadays, so after that we could we could treat proofs as programs and a logical statement as a type. So ultimately then proof of a statement is just a program and that has a type. So Lean is an open source programming language, functional programming language that helps us complement all of this theory. So yeah, so there were a lot of proof assistants that came up during the early days. So as a result of this, proofs can now be treated as code and theorem provers as compilers. So how we would treat a new theorem as something that needs to be proved in that natural language can similarly be translated to be a code, and a theorem prover can be a compiler which when runs the code verifies if it actually runs inside the compiler, verifies that the proof is correct. So Lean comes up in 2013. It was developed by Leonardo inside Microsoft Research, and Lean is still supported heavily by Microsoft Research. So it offers interactive theorem proving. So it's a functional programming language. So whenever you use Lean, you get immediate compile actions. So that makes proving theorems inside a compiler much interactive. And it becomes friendly to not only programmers but also mathematicians. So now, in case of ordinary type systems, we interpret variables as integers or boolean. But in case of dependent types, which Lean uses, we can have types depend on values. So to give a small flavor of how Lean works, let us take a very simple theorem and we'll just go through the proof of it. So let us take this theorem where for any natural number n, we have to prove n plus 0 also gives us n. And we'll prove this by the theory of induction. So induction basically tells when you have n number of objects and it is true for a base case, and it is true for, if it is true for any case, it is also true for the next case, then we can iterate it to be true for all possible cases inside n. So when for the base case when n equals to 0, we have 0 plus 0, which holds by definition. And for the inductive case, let us take for any k, we have k plus 0 to be true. Then we can also figure out iteratively that k plus 1 plus 0 also gives us k plus 1. So it is true for the successor of k. And this is how we prove this statement in natural language mathematical statement. Let us see how the Lean proof looks like. So this is how the Lean proof would look like, and I'll explain how the syntax works quickly. So basically we have two major elements in the proof. We have a goal. So goal is a current sub-theorem that needs to be established. So for example, whenever we define the theorem at 0, it will create a goal that we need to prove. And then we use tactics. So tactics are instructions that we give Lean that breaks the goal into simpler goals and then proves the continuous goals until nothing remains. So for example, in this case, so theorem as 0 starts a new theorem. We define that it is we are proving it for natural numbers, and this is a statement of the theorem that n plus 0 equals to n. We prove the theorem by induction of n. Induction n with is a syntax that breaks the proof into two case files, and for the base 0 case, we prove it by another tactic called RFL, which is reflexivity. And the next one, for the next one, we prove it by another tactic called simplification. So what simplification does is that, so just like how we proved the natural language case, which is by taking the successor of k, we define a successor function on k here, and it proves the simplification tactic automatically proves that if it's true for k and k plus 1, it is true for all n. So all of these syntaxes are like the tactics are something that we built inside Lean. So there are a huge amount of tactics that the community has built, and you can continuously use these tactics to simplify your proofs, and we don't have to prove the same statements repeatedly. So I will also quickly show you how Lean works. So if you are
Can we wrap up?
So if you
One more minute, Sagnik.
Yeah. So if you go inside VS Code and you, downloading Lean is very easy. You have to just use an extension. It will automatically download all your libraries and every battery that you need. It will, if you want, it will also download MATLib, which is one of our libraries that we use majorly. So this is how we write theorems. So every time, so we have an interactive window that is on our right. So every time we write a statement, it shows us what our goals are and what our hypotheses are, what we need to prove. And whenever we use a tactic and it accomplishes the goal, it says that the goal is accomplished and no other goals are remain. So I thought that I would have shown you more proofs, but yeah, that's all. I want to also quickly say some of the major projects that has been proved over the years. So liquid tensor experiment is one of the projects that was started by Peter Scholz, and it was proven by the community with the help of Lean. We have also proved the analysis one is a book by Terence Tao, and it got formalized totally using help of Lean. We have the Fermat's last theorem as a project that we proved through Lean, and so this is the GitHub for the programming language right now. It is at 38,000 commits 2 hours ago. It is a extremely active repository, and we have pull requests that are there are a lot of pull requests that come up every day, and this so what I would say that if this is a programming language or a community that interests you at all, so there are under 10 people who are contributing towards Lean from India. So we are trying to build more and more community based in India so that people can also contribute towards this language. So I'd love to talk to some of you whenever you are interested. Yeah, thank you.
Next, we have Kriyanshi talking about how FOSS is being used to support open science initiatives within the Indian research ecosystem. For example, in planetary science and meteorology, Kriyanshi is a software engineer at Space Application Center.
Good afternoon, everyone. I'm Kriyanshi Shah, and I'm here to talk about empowering open science with scalable interactive computing environments in India. So here is what about me. I'm a software engineer with experience in building large-scale backend systems and developer tools. I specialized in designing platforms for satellite data research and scientific data processing. I'm experienced in Kubernetes, JupyterHub, Docker, Golang, and distributed computing systems for scientific workflows. So here is my question for everyone. Have you ever worked with satellite data, the HDFs? No? Yes, we have one person. So the HDF files, it requires the system-heavy Python libraries, which are really heavy and hard to install. So the HDF files is short for hierarchical data format versions 5 and are a widely used file format designed to store and organize large amounts of complex data, particularly in scientific engineering and remote sensing applications. So the challenge in scientific research is often working and making sense of satellite data is easier rather than spending sleepless nights wondering why didn't that particular library didn't install itself correctly. So our observations that our researchers and scientists work on air-gapped systems. What air-gapped systems are that they don't have internet to them. They are completely offline systems which have zero internet. They can't Google that. That's that simple. So often installing and maintaining all the Python libraries are a headache. Sometimes different environments for different needs, and that too on a machines without internet. So we built something. To sum it up, what I'm trying to say is diverse scientific domains require customized computational environments, and traditional setups are often soiled and non-reproducible. So what problems we are facing at SEC is whenever we have one Python program that we are running in one machine will not work in some other machine. So for that, we created a interactive computing environment that is on a one server running that does not platform independent platform. So the problem was researchers face complex fragmented FOSS workflows. So for that, we created scalable cloud native platform built with Kubernetes and JupyterHub. Onboarding new users, the problem was that onboarding new users to scientific computing tools is time consuming. So that for that, we created pre-configured Docker environments for different scientific domains. And the issue was converting notebooks into shareable applications requires extra coding effort. So that we created notebook to web application conversion via Mercury integration inside JupyterLab. We created a custom Mercury build and JupyterLab extensions to support notebook to web app conversions seamlessly directly from the JupyterHub user pods. So the idea behind it is that we crafted something for our lovely teammates initially, and then we thought maybe this can be implemented everywhere. Because they say that build something you want and then scale it after. So our solution is built on JupyterHub and Kubernetes that offers scalable, secure, and domain customizable computing environments tailored for scientific disciplines such as planetary science and meteorology. Customized Docker containers preloaded with scientific libraries allows our researchers to spin up user-ready environments with minimal technical overhead. So our solution is cloud native in architecture, domain specific. It has domain specific environments. It has enhanced user experience for Mercury, and it has seamless research to app workflow, so that you can share your web notebook to anyone without a scientific background. So the overview is the researchers access JupyterHub via web interface. Then each user session runs in a Kubernetes pod tailored to specific scientific needs. And for interactivity, custom build of Mercury integrates with JupyterLab, allowing users to convert notebooks into shareable web apps. And for scalability, we used micro-K-test Kubernetes to manage container deployment, scaling, and resource allocation. So this is the list of open source tools we used. Because of the help of great JupyterHub community, it was so easy to make this a solution possible. They have a solution for each problem you have. Because we use JupyterHub, Kube Spawner, Jupyter Server Proxy, and JupyterLab right from the JupyterHub ecosystem. And we use Kubernetes, Docker, and custom MLZar Mercury builds and custom JupyterLab extensions to enhance the user experience. So why they are used? So JupyterHub provides a centralized web interface for researchers to log in and access computing environments. Kube Spawner spawns user pods in Kubernetes after authentication, ensuring isolation and scalability. Kubernetes orchestrates container deployment, scaling, and resource allocation for multiple users. Docker to package domain-specific scientific environments. JupyterLab for enhanced interactive computing environments where researchers write, analyze, and visualize scientific workflows. Jupyter Server Proxy we used to enable secure access to additional services within the JupyterHub environment through proxied URLs. And a custom build of Mercury we used to convert JupyterHub notebooks into web apps. And for JupyterLab extension are used to support Mercury inside the JupyterLab and JupyterHub environments. So the architecture is really simple. There is a JupyterHub master pod. It authenticates, and using Kube Spawner, it spawns a custom JupyterLab environments with a custom Docker images, and all that user pod have a mounted satellite data so that users can interact with it. So user flow is for login authentication. Researcher logs into the platform via the JupyterHub web interface. Authentication ensures secure role-based access. Pod creation, Kube Spawner launches a dedicated Kubernetes pod for the user. Each pod is based on a custom Docker image tailored for specific scientific domains. For data access, each user pod is mounted with a shared satellite data volume, giving access to large-scale data sets for analysis. Interactive environments. Inside that pod, we enhance user environments with Mercury to seamlessly work with your JupyterHub notebook and convert it into the web apps. And for the app creation sharing, using Mercury integrations and JupyterLab custom integrations, researchers can convert notebooks into interactive web apps. So for tailored environments, my main focus was on planetary science and meteorology. So for planetary science, our custom Docker images contains KuttyPy, Raster.io, X-Array, Zarr, GeoPandas, NetCDF, and all the libraries. And the GDAL, which is the most hardest to install on air-gapped environments. I cried that night. On meteorology, it's pre-installed with climate modeling tools, data visualization libraries like Matplotlib, KuttyPy, Geoplotly, and GeoViews. So my learnings while making the solution is how to install all these Python libraries on air-gapped machines, which is, once you do it, is easy, but for the initially it's really terrible. And creating custom JupyterLab extensions. JupyterHub has really good support for all the examples and the templates so that you can use and learn from all the templates, and you can create your own custom extensions. And creating custom Docker images which are lightweight in nature and spins up really fast when the user creates. Those are my learnings while creating this. So for enhancing user experience, we've created Mercury integration, RESTful APIs, and JupyterLab extensions. And for future directions, we are planning, our initial thought was to create it for our researchers and scientists. But after some point of time, we thought we can use this environment to share our satellite data so that this platform can be used as a user to interact with our custom satellite data, and we have whole control over the satellite data. So this is our we are trying to do that currently, and for the broader adoption, we are planning to extend the platform to more scientific domains. And for long-term support, we are planning strategies to maintain and update the platform with the current and upcoming libraries. So here is from my side.
Do we have any questions? One question.
Okay. Yes.
Yeah, Kriyanshi, it's just not often that we get to hear about FOSS at ISRO. So can you just talk about like big picture, what kind of things do you use? What is the internal like opinion about FOSS? What does ISRO I don't know, does ISRO want to engage with the FOSS community, etc., etc., etc.?
So I can say about my organization, I work at Space Application Center. So we largely believe in FOSS because we know it is very dependable and we can change the code, so that we are largely we are largely using all the open source libraries. And in my team, my managers and my group heads are really like looking forward, and they choose mainly they choose the libraries and the tools which are open source, because we have more control over it and we can contribute to it. So I can say we are more FOSS focused, but sometimes there are not tools available which are open source. So then we have to create our own tools, and we can't share it, most of the internal tools we use, but we largely use open source tools, and then we mention it and they support it anyway. They mention it and they help I'm recently working on a scheduler project, and my managers and my manager, we all are literally talking to the maintainer and helping him creating PRs and merging our PRs, and we are actively contributing to FOSS. We don't mention it on like a publicly level, but we try to do whatever we can.
One more question. No worries. So you mentioned that you were working on installing these Python libraries in air-gapped systems.
Yes.
There is also certain concerns with open source packages with respect to security. So how do you people scan for those securities? How do you make sure that whatever you're installing in your systems is safe to install without malicious code? Is there some pre-scanning happening, or?
So we have some list of libraries which we can use. We have internally, they can flag green or red that you can use this library. We have own pip served inside. We are doing it we're doing it for us. But yes, we largely what we do is we install libraries on an internet machine. Then we check it, it's that problem with it, and then we shift it to the air-gapped systems. That's what we do right now.
Okay, so you install it, then you scan it on your own, and then you have your personal self-hosted pip that you use internally.
We have some mount points.
Stuff,
we can shift it to that
fair.
machines.
Thank you so much.
Next, we have Agriya, who will talk about use cases in science communication and science policy using in-browser FOSS tools. Agriya is a software engineer at Quantsite and works on Pi, Iodide, JupyterLite, and other open source scientific software projects.
No, set up speaker view. Okay. Yeah. Yeah. Right. Okay. So just this, I think. Yeah. Why is it supposed to be? Maybe. Yeah. Okay. So when I choose a window and I mirror the window, it's still skewed. I want it to be, yeah. Okay, so just like this. Yeah. I think we'll just need to like stop mirroring, and then should I change the display to
Sorry, I'm
something
not very
else?
compatible with Mac. I'm just like used to Windows and all.
Oh, okay. So should I get this done on some person?
Hi everyone. So I'm here. So when the dev room will end, like in the ending 5 minutes, we will kind of give you sort of like an introduction to a conference that we are trying to do nationwide SciPy India, and we have like a feedback form for this dev room, and also like a initial survey form for SciPy India, just to get like what's the opinion of the community and the interest. And yeah, so just like stay back please. Yeah.
Oh, it's on a link, so I can open the link tab. Sure. No problem. So
Do you need sound?
no, I don't. No, it's slides.com. I'll just wait until I open it before you add it. Do we still have time? Because we had some buffer time, right? Okay, and this time this should be the entire screen, or okay. And what if I do this? I think
I think it's something to, because even on my computer it's getting switched to. So I think it has a computer issue.
okay.
But shall we start anyway?
we should. Yep. Okay, so hi all. This is a talk about using in-browser free and open source software tools for science communication and evidence-based environmental policy. So it's a really short talk that covers up a lot of the discussions that have already taken place with other talks. So it's sort of also a supplement to those talks. At this time, this is also in some ways a call to action for doing better science communication, and also it is a means to like it's also a rambling for me for just spreading the word about the projects that I maintain. So here's a little bit about me. I am a software engineer at Quansight, and I usually like doing Python packaging and distribution. I like the documentation, but recently my interests have also been piqued by interactive and numerical computing. And I am involved with a few packages and libraries, in specific Pyodide and JupyterLab, and I'm also a member of other open source organizations. I'm focused on scientific Python. So just to get to the crux of my presentation, what I want to talk about here is that we're doing science communication in a very poor manner, in the sense that there are a lot of structural barriers to science communication, whether that's, let's say, monetary barriers. Let's say you don't have the right level of funding required to do proper science communication, or let's say there are, in these cases, ideological barriers. So even though you are like scientists, or even though you have like so many people who are reading about science, you are still commit to not doing anything about superstitions. And then this is also something that ties into stubble burning, for example. Stubble burning is a highly politicized issue in India at this time, especially because of how it is perceived to cause pollution in New Delhi. And it's said to originate from Punjab and Haryana. And what I would like to emphasize on this aspect is that stubble burning has actually reduced by 71% in the last 5 years since the pandemic happened. And as this time, it contributes only around 0.92% of all the air pollution indicators in the entire, basically all over the year in New Delhi. So all of the air pollution that you're seeing in New Delhi is being caused by vehicular emissions and emissions from industries. So you can read the report for you can read this report to know more about it. Also, what this does is that it overshadows real issues that we should be thinking about. For example, at this time, Delhi's air is poisoned with mercury at a level that's much, much higher than other cities, and even in other cities, it's much, much higher than what the safe standards should be. So what this usually does is that it derides data-driven policy making, or basically it leads to the lack of data-driven policy making, which means that resources are misdirected, which is why, if you have, let's say, the media talking about issues that are not pertaining to, that don't pertain to such problems, then vulnerable communities are disproportionately affected. So, and also this means that people think that scientists do not do anything, because at this time, scientific institutions are basically, so public trust in scientific institutions erodes as a result, because there's no solution to air pollution if you're not tackling the right problems. So just to get back to the technical elements of my talk, there's this project called Pyodide. It's a port of CPython, the Python programming language, to WebAssembly. And basically, it supports a lot of scientific Python packages. These fundamental packages, which I've listed here, these allow you to use various other packages in, let's say, the geospatial area. And there's like hundreds of packages and libraries compiled using the ImScript and compiler toolchain.
And you can install a lot of these packages as Pyodide wheels, which is basically the format that's used in Python packaging to install binaries. So similarly, this has been talked about by Arjun in his talk quite to quite an extent. This is JupyterLite. JupyterLite is also a project which is basically WebAssembly powered Jupyter that runs inside your browser. It's reproducible by design because all of the code data and all of your configuration is stored at a hosted static location, and also that it is by extension using Pyodide for as the Python driver inside, as the Python kernel inside for your Jupyter environment, which supports log files by default. So as opposed to Jupyter Hub, it is deployable using static website hosting providers, so whether through GitHub pages, Cloudflare pages, GitLab pages, and so on. This is what I feel is can be used to establish a new brand of interactive computing based on small data. And what I mean by small data is particularly data that is smaller than, let's say, 1 GB that you can operate on within the confines of a browser, which means, let's say, being able to run through some basic data analyses on CSV files or Parquet files, or basically on, let's say, GeoJSON files. And basically, my talk is also a call to action in this regard, using FOSS in browser tools to be able to use channel resources towards science communication. So there are a bunch of apps that use Pyodide and are based on the JupyterLite ecosystem. So there's Voicey. Similar to Mercury, the tool that Kriyanshi mentioned is for basically creating web apps from Jupyter notebooks. This is, it can be used to create apps that are run statically inside your in the browser. And similarly, there's Dataset Lite that also uses Pyodide for small data use cases. And then there's Panel, which is like a very heavy-duty application for data exploration and dashboarding, but it can also be used with Pyodide. So there's a lot of new stuff with Pyodide. So right now, we in this year have enabled new packages, not us, but a lot of our contributors. So you can now establish much more refined standards for high performance use cases. So you can use small data even better nowadays using PyArrow, DuckDB, and Polars. Similarly, improvements to the WebAssembly standard across browser conventions means that, in particular, JavaScript promise integration is now available. It is the default in Chrome 137. This allows you to run synchronous Python code with asynchronous JavaScript web APIs. And this allows you to work with a lot of packages in the geospatial area to now be able to work on basically what is the web loop. The web loop is where is the main thread main event loop that's Pyodide's equivalent of the standard conventional thread loop. So thanks to all of our contributors for their hard work. And to you, the viewer, it's a talk about, consider this as a talk about using in-browser frameworks to build civic tech initiatives. And also it sort of tries to reiterate that a lot of data work nowadays does not require HPC workflows, especially if you're working on small data, because there's like in-browser tools that you can use without provisioning a server. And WebAssembly, I believe, can be a first-class format for in-browser scientific workflows. And I would like to just advocate for doing that. So thanks for your time. I hope you like this talk. And if you have any questions, please let me know.
We have time for some questions. Okay. Thanks, Agriya.
Thanks.
Next. next, Aftab will tell us how he's using FOSS observability tools to perform telemetry on scientific experiments. Aftab is a DevOps engineer and an active contributor to the Grafana ecosystem.
I'll connect the HDMI directly. Hi everyone. Malayalis. Yeah, I mean, I have been talking to a few people downstairs, and I was just randomly saying, I've seen more Malayalis here in Bangalore rather than in Kochi. So, yeah, thank you all for coming, and thanks for tuning into my talk. So, my name is Aftab. I do DevOps for a living. For fun, I do organize meetups. I do attempt a few, stand-up comedy, which is basically the same thing. You try to make people laugh by hoping that they learn something new. Yeah, so usually I talk about containers, DevOps, CI/CD, all those things. But today I'm thinking of going off script. So yeah, let's talk science. Science is, it's supposed to be exact. It's supposed to be, it needs to be perfect, right? But in real world, it's not. It's messy. So just imagine you have an experiment, but you cannot replicate it, reliably. But what's the problem with that, right? You create a few experiments and you try to replicate it, but it fails. The problem is, the findings related to those experiments, it becomes really questionable. Now, this is how modern science is today. I mean, we all have that naming convention, that weird naming convention that we use for our codes. This is kind of similar, just that they are facing it very badly. Now, most of what they create is not 100% reproducible. It's more like, what do you say? If you, you run a code, it works for you once. But if someone else runs the same code, it fails. But that doesn't mean the whole thing that the initial person did is wrong, right? So this, in our world, it's called a bug. In this world of science, it has another name. It's called the reproducibility crisis. Like I mentioned, over 50% of the published findings are, it cannot be reproduced. So that is actually a problem. So yeah. Now, I would like to, it's more like an illustration that I made. So science also has a workflow. So you start with a theory or a hypothesis, you experiment it, you collect the data out of it, you analyze the data, then you publish it. Now, after publishing it, there is a few people who does a peer review, and they try to replicate it, right? They try to replicate whatever they found through the publishing. Now, if that fails, again, the findings that they made is going to be a problem. Now, after that, they refine it. This is a continuous loop. Now, have you seen this loop somewhere? Yeah, I'd like you guys to say it out loud. Yeah, it's actually DevOps. So that's what I was trying to, bring into. Science has been doing DevOps for a while now, but just that they don't use version control or let's just say containers or anything. It's just that they weren't using the right tools. Now, recently, not recently, people in research field or scientists have started adopting DevOps practices for scientific research. And they also have a name. And it's funny how people come up with names so easily. And yeah, it's called research ops. Yeah. I mean, it's actually fun. But when you think about it, research operations, yeah, it's basically DevOps for science. Now, how these things are mapped, right? Git, for us, it's used for versioning code. We used to version scripts, but in terms of, what do you say, in terms of scientific domain, it can be used to version manuscripts, data sets, or, just documents. People, send emails regarding findings and all, but if you want to go and replicate the same finding once again, they'll have to scroll through emails. Instead of that, just push it to Git. So that's what they do. Now, Docker is actually used to package the whole environment. I mean, say, computational fluid dynamics. I mean, I was very bad at it. Anyways, so you'll be able to package the whole environment and share it to someone else so that they can experiment or reproduce the whole concept once again. CI/CD is there. It actually is more like a heart of this whole thing, because no student wants to run a 20-hour-long pipeline 20 times, manually. So that's another thing. Kubernetes actually plays a very vital role in this whole research ops concept, which I'll come to it soon. Kubernetes, there are multiple workloads in high-performance computing systems. So they require scaling things up and down pretty much instantly and more efficiently. So that's where Kubernetes steps in. Then there's Prometheus and Grafana. I know my talk is about observability, but this is going more out of observability. Anyways, Prometheus and Grafana can monitor pretty much everything. I mean, it's like more like a match made in heaven, if you want to put it like that. Now, I have just mapped everything, almost every tools that we commonly use as DevOps engineers to how researchers use. You want evidence? This is your evidence. So you can see CERN. How many of you have heard about CERN? Yeah, the LHC guys, people who shuts down their whole operations for like a few months and then they'll come back. You know what they do while shutting down? They actually, update their clusters. They update their servers. Recently, a shutdown was actually meant to migrate all the virtual machines to Kubernetes clusters. That's how they use it. In biology, to be more precise, in genetic engineering and genomics, people use Git and other CI/CD tools for a better thing. They also have a name for it. It's called BioDevOps. I know, funny, right? Now, then there is Git used for research projects. There's Grafana and Prometheus and other things used to monitor plants. I mean, monitor plants. Then there is Docker for genomic workflows. They package all the workflows together and you just publish it. Then there's Terraform, who comes in and goes. So, with that being said, what I'd like to say is, if DevOps helped us debug Kubernetes or something, maybe, just maybe, I'm not saying it would, but it could help us debug the universe. It's just the same tools, but a different use case, right? But that doesn't mean it does not come with challenges. It does have challenges, mainly, cultural and technical. In terms of cultural, you cannot expect a scientist to learn all the Docker commands or the Git commands right away. Right? I mean, they cannot. I mean, most of the researchers still use their personal diaries as lab notebooks. So there's that. Then there is technical. High performance computing systems and legacy messy systems does not actually play well with pipelines, cloud-based pipelines now. But then again, DevOps was once hard, and it still is hard for a few, including myself. Uh, so DevOps helped us solve the problem with collaboration, automation, and all those things. Now, Research Ops is on the same path. It could solve this whole problem. So next time, when you think about DevOps, think about servers, think beyond servers. You know, maybe science, maybe how to track your Bumble profile. I'm not sure if someone gets that. So yeah, since this is a science-based talks, I had to go through a lot of research papers. The last time I went was like 2 years ago. Feel free to go through that. So yeah, thank you so much for listening. And if you want to talk about DevOps, science, or just grab some food, hit me up. Thank you.
We have time for maybe one question.
Hello. So I used to work in a computational material science research lab as a student. Okay. So what I noticed was like there was no awareness about. So we used a simulation engine. Okay. And where we had to create input files and submit it. When like the people before me who were working there, they had like each file, successive file, they used to create like 20, 30 versions of it. And like they had no awareness of Git and all that kind of stuff. And like when I learned about Jenkins, I realized I could create the whole pipeline for my thing. So what my question is there any push from like in Indian institutes, are you aware of any push towards people learning about DevOps and implementing it in their research? Because a lot of repetitive work is being done for like no reason.
Yeah, what was your name?
I'm Vinay.
Vinay. What you said is absolutely right. And to be frank, I also came across this whole topic a few months ago. I was just having a personal project on monitoring plants. So that's how I got to know how DevOps things are being used here. I mean, in the evidence, and to the answer to your question, I'm not sure if universities actually know about this, but there are a few platforms like protocols.io. I just found them on YouTube, so you can just check that. I mean, it actually promotes all those things there. I mean, then again, yeah, it's something you can explore on.
This isn't a question, but a comment. It's people like us who need to go and tell the science people that, hey, look, there are tools that you forgot about. We will come help you. Places like this are the right place to have these conversations. And then, yeah, the science people left alone, they'll happily continue doing science and keep doing manual work. But yeah, when we know the right tools, it's our, in my personal opinion, duty and like responsibility to go and tell these people.
That's what he said.
Next, Alosh will help us look under the hood of some LLMs and help us understand FOSS evaluation tools for the same. Alosh is an AI engineer at Discern Security.
Hey guys, good afternoon. So my name is Alosh. I'm an AI engineer and a researcher, part-time hobbyist as well. And I know it's almost time for lunch, so you guys might be hungry, but I'll keep it as short as I can. So I'll be exploring transparency in LLMs, basically trying to use open source tools to peek into the reasoning happening under the hood of different large language models. So this is usually what happens when we have a conversation. We don't know what's going on in the person's head. So I don't know how you guys are feeling about this session, and you guys probably don't know what I'm thinking about when I'm speaking out to you guys. But what we do know is what comes out of the mouth is probably the reasoning of what happens inside your head. And the same is the case for LLMs. So we never really see how LLMs think. We only see the response. We never really know, like, okay, what are they thinking about? Are they thinking in English or in Hindi or in Kannada or Malayalam? We'd never know that. And the reason is because LLMs are a complete black box. And all we know that under the hood, they look like a bunch of neurons. And the question that's always struck me is, what's inside the box? This scene, you might know this from the movie. I don't know how many of you guys know it. Okay, yeah, there are some people. It's a very dark scene. But yeah, the question is, what exactly is happening inside this black box? So just a simple question to the audience. What's the answer to 13 times 13? Okay, could someone explain the reasoning for that? Anyone? Okay. Let's assume this is a second grade math class, and I'm asking you to multiply these two. 3 3s are 9. Okay. And then 13 apples 13 times. That's what he said. Okay. That's it? That's it? Okay. Tens place, same thing. Okay. So I've got an idea of how you guys are multiplying 13 times 13 in second grade, but now I guess it's all a guessing game. So in LLM, it's the same thing. We ask it the same question, what's 13 times 13? It gives us the answer as 169. But we don't know what's happening under the hood. It's a complete black box. We don't know what the neurons are thinking about it. But what we can assume is that it thinks in almost the same way that we thought. So let's say it's going to think, someone said 3 times 3. So it will multiply 3 times 3. Then it's going to multiply the tens place. And it thinks that, okay, it's somewhere in the vicinity of 100. And then it's supposed to be a square root. So that is greater than 100. And so it guesses, okay, so it's a number that ends in 9. And it's supposed to be a square. It's greater than 100. So let's guess, 121, 144, 169. So what happens under an LLM is that it's a complete guessing game. But we need to peek further beyond guessing to see what really happens. And that's where something called circuits comes in, not your physics circuits, but circuits in reasoning. And in fact, this is an actual LLM's reasoning circuit. It traces the exact path of how LLMs think. When you ask it a question, what are the exact regions it goes through? What does it exactly think about? And where does it concatenate all this information to give you a solid answer? And we can also trace the circuit of reasoning in vision models. So for example, this is CLIP. CLIP is OpenAI's vision multimodal model. And it thinks not in terms of text, but in terms of images. And when given the word India, this is what its neurons thought about. So it's all pictures of, you can look at the faces, look at the logos, the architectures. It's all very sort of akin to Indian architecture because it's learned on this data. And if you were to give Bangalore, it would probably give something like this, just my assumption. Traffic, the food, Uber, all that stuff. Transformer Lens is an open source library. It's a tool to peek into how LLMs think. And it's I'd say it's pretty apt at just breaking open the LLM and seeing how it thinks. Another question. In what year did World War II end? 1945. So some of you know about it because you've learned about it somewhere. But from an LLM's perspective, when we ask it the same question, it thinks in different formats. So for each option, it creates 3 different paths. And one of these paths has the highest probability of being correct. And boom, it selects 1945. Now, how do we see this? How do we know that it selected 1945? Not because it was trained on it, but because it was able to think with precision that it was correct. And that's what Transformer Lens does. And just to get a bit technical, this is an attention heat map that shows us how relevant different words are. So the more yellow the words or tokens are, the more relevant they are. The more blue they are, the less relevant they are. And this is sort of like a low-level view of what transformer lens gives us. Now remember the India-Bangalore scenario. So that's a vision-based approach. So we have Prisma 2. It's an open source tool for visualizing neurons for multimodal LLMs. So for example, this is an image of a cat. And an LLM can accurately identify it as a cat, of course. You can see these little emojis in the second picture, right? So that's the LLM like pointing out like this is a cat and this is not a cat. So when you use Prisma, Prisma goes into each layer of the large language model and sees the output. So in layer 0, it's a complete mess. It doesn't identify cats. If you go to layer 7, it's trying to get a sense of the picture. And as we progress and reach the last layer, it's able to find out that, okay, the LLMs is spotting this as a cat. Now, towards the end of this session, you guys might be having these thoughts. Like I've talked about circuits, some lens stuff, prisms, but what might be coming out of your mouth is maybe it's cool, it's awesome. So what if you were able to be like this guy? You might know him, X-Men, Charles Xavier. So we don't have like an open source version of this guy yet, but maybe if Neuralink is successful, we'd be able to tap into people's heads and see what's happening inside. But sadly, fortunately, we only have the resource for looking into LLMs. And that's the end of my talk. And I just want to shout out to Tinkerspace, who have been generous to provide me a GPU to test out Transformer Lens and Prisma. And if there's any questions from your side, I'd love to entertain them.
We'll skip questions. Can we have questions after the entire thing is over?
I think there's one person.
Can we have questions after?
Okay,
Thanks.
sure. Thank you.
Next, Jigyasu will give insights about benchmarking time series estimators with SKTime. Jigyasu is a contributor in scientific computing and data science ecosystem and an active developer of SKTime.
Hi everyone, I am Jigyasu and I am an undergraduate at NITA and also I have been recently made a core developer at SKTime. Thanks. I'll be talking about, I'll be very briefly talking about benchmarking time series models with SKTime and how SKTime makes it easier and efficient. So the first question that should be in your mind right now, and I expect you to be a bit familiar with time series models if you're attending this talk. The first question that should be in your mind right now is that why do we need to benchmark in the first place, right? So in the recent years, there has been a explosion of time series models. So if you look at the evolution of how like time series models like practically came into being. So in the 70s and 80s, there were a lot of statistical models like ARIMA, SARIMA, the exponential smoothing family. And then later in the 2000s, people started adopting machine learning models like random forest and all of that. Then came the deep learning boom around 2014. People started using CNNs and LSTMs. You probably have might have seen a lot of stock prediction projects that undergraduates make. They use a ton of RNN and LSTM into their project. I have always wondered if they really did accurate stock prediction, why are they still in the college and not on a like ship or something? But yeah, then in the 2020s and after the ChatGPT era, there was a lot of foundation models that started popping up. Kronos, Moirai, these were Kronos from Amazon Research, then Times FM by Google. So we started seeing a lot of these models that started popping up in time series domain. So it gets very difficult to really understand which model is good for our use case. So benchmarking, basically time series is used in a variety of sectors, retail, healthcare, energy, and as we have seen in the previous talks, in scientific research as well, that bird talk, the people were analyzing time series data on birds. So yeah, we see a ton of time series uses, and it gets very important to know which model works on our use case. And as contrary to what marketing claims that newer models are always better, I think it's the performance of those models often varies across data sets, domains, and metrics. So it gets very important to benchmark our own, benchmark for our own use case. So yeah, basically the benchmarking helps us answer two important questions. Which model actually work for my use case? And since foundation models are very expensive to train, are they even outperforming the statistical baselines on my own proprietary data sets? So how does SK time come into play and helps in benchmarking time series model? So I'll first give a brief introduction about SK time. It's an open source, free to use, and community governed time series machine learning framework. It has a scikit-learn like API. So if you're very familiar with scikit-learn, you'll find skTime quite familiar as well. So if you're used to fit and predict methods, you'll be very familiar with skTime's API as well. It has a BSD3 permissive license, so anyone can use it freely without worrying of any copyright claims or whatever. We are in a FOSS conference after all. Anyway, so another cool thing about skTime is that we have I can claim this very openly, we have the largest model zoo. That means you can expect models from 1970s, 60s, and you can expect models from research conferences from late 2024 and early 2025 as well. And they all have a very consistent API. So you can find this estimator overview page on our docs, and you can look up for, it's kind of a marketplace where you can look for any models of your choice. And we do not only provide the models, we have dataset loaders for majority of the popular time series datasets in both classification and forecasting domains. So, and they are, so these datasets are in different formats, right? And to use them consistently, you need to have them in a consistent in-memory data representation. So our loaders convert all those like hundreds of datasets in skTime compatible in-memory representation. So I think that's another cool thing about using skTime. Then we come with why how skTime helps in benchmarking. So as I previously mentioned, skTime has a consistent API across all models. So if we in the examples, you can see a foundation model. Basically, it's Kronos, which was recently released by Amazon Research Labs. It has the same interface as that of the naive forecaster, which is a statistical model probably from 60s or 70s. And they have a consistent model. So you don't have to change anything if you want to change your model. If you want to try different things out, you just have to change 2 or 3 lines and you're done. You don't have to worry about recreating the entire research interface or whatever. So 2 important things that's important with any benchmarking model is interruptibility and reproducibility. So as a few talks before, I think it was Aftab who talked about reproducibility in science. So we already know how important it is. There are numerous papers popping up every week. So they need to be reproducible, right? So if some research paper on time series claims that their model is topping some leaderboard, we need to check if it really is that good on our data set in our use case or not. So, and yeah, and the ability to reload from an old state is also very important. So let's say the experiment is broken in between, the module should be should be able to load from an old saved state. So we have this ability in skTime currently. Benchmarking is performed in skTime across a combination of estimators and tasks. Estimators is basically the models, and tasks can be datasets, metrics, cross-validation strategies. So let's say if you have one model and like 150 datasets, so it would be the one model will be run with all those 150 datasets, and if for the like same way with metrics and cross-validation strategies. So I just have an example run. I cannot probably explain every object in it, but I'll just show how easy it is to benchmark with skTime. So you first instantiate the object, you add the models, there's a benchmark object, you just add the models to it, and then you add the task and get the result. It's that easy. So yeah. And what's next? Currently, we are, as I talked about reproducibility, currently we are working on something called collections. So these collections are basically sets of predefined models, predefined data sets, metrics, cross-validation strategies. Let's say a paper came out. So Bake Off is a paper in time series classification domain that's very popular and often cited. So let's say you want to reproduce the Bake Off paper or want to extend it, you will need to like import all those 160 data sets in a consistent format, all those 60 models used in that paper in a consistent format. So we have come up with this concept called collections, where you can just, so we have a proposed vignette for the collection objects, still not released yet, so feedbacks are appreciated, of course. So it would be a predefined collection. You can just load it and add it to the benchmark and get the benchmarking results. So it's that simple. Let's say, and it's also it can also be extended. So let's say if you are academician and you want to test your own algorithm, you want to see how it performs on an established study. So you don't need to set up an entire experiment on your own. You just need to load a collection. You can just extend it by adding your own algorithm, and that's it. You can get the entire benchmarking result. Or if you are an industry practitioner, if you're a data scientist at an industry, and you want to see if a benchmarking study claims something, it really works on your own proprietary data set, you can just add your own data set to it, to an existing collection, and you can run the benchmark. So yeah, I think that's it. Thank you very much for listening, and we always welcome new contributors. There's the QR code for our Discord community. Feel free to join in, and if you want to contribute, feel free to contribute. I'm open to any questions now. Yeah, sure.
Okay, it needs a hard press, sorry. What's your recommendation for a good data structure or a class or a type or something which works with uniformly well with something like skTime and with stats models?
Yeah,
so what I mean is I often find myself going back and forth between using a pandas time series, but that fails in some really weird scenarios because SK compatible stuff expects numpy arrays, and although they may be similar, they're not the same. So what's your recommendation for something that's very compact and where I don't have to manage my timestamps and my values separately?
There are two different layers. The first is how these data are stored on the drive, like on the hard drive, and the second is the in-memory data representation. So the hard drive thing, we don't control it. It's from the like provider of the data set. We only control the in-memory representation. So we have these utility functions. So we have something called mtype, with which we have like made it very strict that we only work with this. So if it's a hierarchical data set, we use something called PD multi-index hierarchical. Like we have several of these mtypes, and we have these converter functions that convert a given data given memory represent is it's a NumPy array, it can convert to R format, and the loaders we have, it converts those data sets by default. So yeah. Yeah, it's just a M type, so you can use something called to that, and yeah. I'll talk to you if you want to talk to me. I'll talk to you. Thank you very much.
Hey guys, just before you head out to lunch, I know everyone's eager to go there, but I won't take much of your time. I just wanted to introduce you to the SciPy India community, which we are building. So you might have recognized most of the folks here. We just give talks, Agriya, Aditi, Malaysia, etc. It's not working. Yes. Yes. So this is a community-driven initiative promoting scientific community in India, part of the much larger SciPy ecosystem. We just revived it. We had our first virtual conference in the month of July, and we plan to continue hosting, be it community calls, be it workshops, hopefully a conference either later this year or early next year. Right. We encourage contributions in free and open source software. I know most of us did talk about that. Most of the talks were revolving interactive computing in general. So if you could just take a picture, this is our community. We have a Zolib chat set up. Yes. Folks who want to volunteer, please reach out to us. We do have the contact slide coming up. So if you're interested in scientific computing, just reach out, and yes. If you want to take a picture of this, be it our website, GitHub, everything is open source. Our calls for proposal site is also open source. We believe in keeping reviews public. I believe we had a lightning talk about that yesterday on keeping the review proposal public in general. I'd really appreciate it if you could scan this QR code. This is our feedback form. So it contains questionnaire on where you think our actual in-person conference should be, and a couple of other questions relating to the community. And I'd really appreciate this if you could just scan this QR code, take a picture and fill it out in your free time, but yes. That's it, thank you. Thanks for staying up till the end of the whole session and the dev room, but yes.
It won't take. Yeah, it won't take more than a minute to fill the feedback form. Thank you.
She's the one who created the form, so she's emphasizing on it, but yeah.
And just a small thing, we would also like to thank FOSS United for this, because they were the ones who provided us with the necessary infra for the first community call that we had back in July. So for live streaming and for doing our CFPs and just our event registrations. So I hope you will register, and hopefully we'll have a conference in late 2025 or early 2026. Thanks.